So shall we begin?
Yes, I think
Okay.
let us begin.
Yes,
So
please.
good morning and good afternoon to all the Japanese colleagues, and welcome back to the second day of the workshop. And we will begin our session with the standard model and beyond. Okay, so let us begin our session with the Professor Osamu Jinnouchi. So he will be talking about the beyond standard model searches at the LHC experiments. So Professor, you have 25 minutes plus 5 minutes question answer sessions. Okay, thank you.
Thank you. My name is Osamu Jinnouchi from TokyoTech. The topic of my talk today is about the particle physics, especially the collider physics. The title is Beyond the Standard Model Searches at LHC Experiment, and I'm very honored to give a talk in this workshop, and I'd like to thank the organizer for the invitation. Okay, so let me start with the composition of the fundamental physics experimental groups. So we have these 7 groups inside for the fundamental physics inside the physics department. We have the nuclear science, nuclear physics, and particle physics, and astrophysics and cosmologies. And let me start with Professor Kuze. He's working on the neutrino experiments, hyperkamiokande and also superkamikande. And also he's working on the collider experiments, LHC Atlas. And also myself, Jinnouchi, is working on the CERN LHC Atlas. And the beyond standard model searches is the topic of today's talk. And Professor Kawai and Professor Yatsu are working on the astrophysics, and they are looking into the cosmic ray, gamma ray burst, and black holes, and so on. So with the telescopes and satellites. And Professor Somiya is working on the gravitational wave detections at Kagura in Japan. And so the 2 professors from nuclear physics, Professor Fujioka is working on hadron experiments at J-Park in Japan, also GSR in Germany. And Professor Nakamura, he will have the talk on tomorrow, and he's working on the neutron-rich nuclear experiment at RIKEN. So let me start with, before going to the beyond standard model, let me briefly show you the status of the Higgs and the standard model. So Higgs is considered to be the origin of the mass. So this is a cartoon showing the before and after the electroweak symmetry breaking. So before the symmetry breaking, all the particles are massless, and after this, the time of 10 to minus 12 seconds, there was the spontaneous symmetry breaking occurred, and then Higgs field which is a vacuum state, has the vacuum expectation value of order of 250 GeV, and this made all these particles, leptons and quarks, and part of the gauge bosons to be massive. So the finding of the Higgs boson is the key for this to understand this mechanism. And so the discovery of Higgs was done in 2012, and at that time we found the new particles, but it looks like the Higgs, but we were not so sure. After 1 year of study, it was considered to be really the standard model Higgs in 2013. And this is the highlights of the such studies. We look into the Higgs to gamma final state and Higgs to 4-lepton final state. You can see the clear peak around 125 GeV of the invariant mass distributions. And also you can see the clear significance over 5 sigma, so that we could declare the discovery of the new particle. So for this, we use the facilities called Large Hadron Colliders. located at the suburb of Geneva, Switzerland. And this the Large Hadron Collider is installed in the 100-meter underground, and there are 4 experiments at the interaction point of this LHC, and our detector Atlas is located in front of the CERN area. And this Atlas is the gigantic detector and composed of the several detector components. And from inside, we have the tracking detector to measure the charged particle tracks. And second component is the electromagnetic shower calorimeters, and which measure the shower of the photons or electrons. And the third component is the hadron calorimeters to measure the jets and the missing momentum of the events. And also the last part is the so-called muon spectrometers, which measure the momentum of the muons which penetrate the detector. And as you can see that with the one collisions, there are many collisions occurs because of the huge number of protons inside the one bunch. So with the one bunch crossing, we expect about 50 interactions currently. And then we can see the many charged particle tracks like this. So the detecting the particle charged tracks like this are very important. And from TokyoTech, we have 2 groups joining this experiment. And our group, Jinnoji group, is working on the inner trackers, and we are working on the data quality of the current detectors, and also we are now preparing the hardware upgrade for the high luminosity LHC, which start from 2027. Oh, by the way, I didn't mention that. Let me go back 2 pages. So we have the 2 runs so far. Round 1 was 2010 to 2012, and with the 7 or 8 TeV of collision energies. And from round 2, in round 2, we have 4 years running, which were 13 TeV of the collision energy. So currently we are in a shutdown mode, and we will resume our run 3 from 2022. So, and the Kuze group is working on the trigger, high-level trigger for the muons, and they work on the trigger algorithm upgrade and calibrations, and also the new physics menus for the various physics processes. So just give you the highlights from the recent news for the Higgs physics. Left-hand side is the coupling strength measurement versus the particle mass for the different particles. And if the Higgs mechanism is correct, then we expect the coupling strength is proportional to the mass of their particles. Then, as you can see that so far, all these measurements are following the standard model Higgs predictions. And these are for the gauge bosons and also 3rd generation quarks and 3rd generation leptons. And nowadays we have also the new entries for the 2nd generation lepton, which is muons. And this is a currently ongoing effort. And there's so that this year we published. Actually, it will be published next year, next January. But it is a Higgs to 2 muon decays, and it is a very, very rare decays of branching ratio of 10 to minus 4. And so currently we have this size, this amount of events, which is very small, but we see the observed significance of 2.0 sigma for the background only hypothesis, and we need more statistics to complete this project. So for the standard model, there are lots of precision measurements performed during the last 10 years of LHC running. And this is a cross-section times the many various production processes. And nowadays, we also have the processes including the Higgs. And so these are very small, but and then these colored points are the measurements from the different collision energies or the different colors. And these gray rectangles are the prediction from the standard model. And as you can see, that theory is well produced, well confirmed by the measurements over the 14th magnitude of the cross sections. So we can conclude that so far standard model is well behaved within the 10 years of LHC data. Now moving on to the beyond the standard model. So as we saw that standard model is well extremely successful, but there are two big issues. One is that we are lacking the candidates for the dark matter of the universe. We know that our universe contains 25% of the dark matter, but the standard model is only can explain the 5%. But so this dark matter is not explained by the standard model yet. Then there's also we discovered Higgs, but Higgs mass is much smaller than the calculation from the standard model. And so if we believe the standard model is correct, the Higgs mass should have been 10 to 13 times larger, which is not happening. So there is a big mystery. And so that since the standard model is confirmed with the super precision, so this is a big contradiction. And so new physics is necessary, and we look into the beyond the standard model. So one of the strong candidates would be the supersymmetry, which predict the new sets of particles called the super partner of the standard model, which differ from the standard model particles by a spin of 1/2. And there are several candidates for the dark matter. So these has to be the neutral and also has to be heavy. And there are a couple of them. Also, by assuming the new sets of particles, this Higgs mass problem due to this loop diagram from the top quark can be canceled out by these new Suji top particles. So these two problems can be solved, but also we can open up the new possibility for the new concept for spacetime, which is called super spacetime, and also the unification of the three fundamental forces. So now typical signatures, how they look like in LHC. So when the proton is collided, then we expect the Suji particles to be produced in pairs, and then they decay into the lighter Suji particles, ejecting the hadron jets like this, and also leptons. And finally, the lightest lightest Suji particles will be stable and escape the detection. So inside the collider, we would expect the large momentum jets, multiple jets, and also the large momentum missing particles like this. So we look into such events. Over the last 10 years, decade, we had the many events. So let's say 1,500 trillion of events. We can apply the very harsh event selections, and then the main event is like this. So this is a histogram distribution of the energy sum of the events, and colored histograms are the standard model predictions, and points are the data. And if the Suji exists, we would expect some distribution like this dashed line. And this area is in the tail, and we are lacking the statistics, so that we need more statistics to find this. But anyway, yeah, we need a huge statistics needed for the both data and Monte Carlos. So this is the current situation in the Suji searches with the particular channels. Left-hand side, the Greeno production, which is a super partner of the Greeno. And this is a round 1 result, and this is a round 2 result. And we could extend significantly from round 1, but now we have excluded the mass of the Greeno up to 2.2 TeV, and so this region is excluded. And for the top SUJI top productions, we could exclude it up to 1.2 TeV, and so that with SUJI production via the strong coupling is now severely constrained. So the strategy of a group is that so far no significant excess has been observed in these such major channels. So we are looking to the different way. And by the way, the SUJI cannot be too heavy to realize the cancellation for the Higgs mass, so that we expect the SUJI to be not heavy. So if a SUJI exists, so there we can expect 4 scenarios. First one, if the SUJI exists, but mass is a little bit larger than the current limit, and then we can just continue the current searches with a larger statistics. But our target is the second and third. So if SUJI exists, but they are only producible via the smaller cross-section processes, then so we are looking into this, and we are looking into this electroweak production. So third case is that SUJI exists, but they are hidden in the different phase, difficult phase space for the detections. So for this, we need to invent a new technique to look into the non-conventional signatures. And the fourth scenarios, currently we are not thinking about this, but SUJI does not exist. So, so electroweak productions, which is 2 or 3 order of magnitude smaller than the Carl-Strong productions. So we are looking into this, the Gagino pair productions, and which have the smaller cross sections, difficult to find, but they have the clearer signatures with less number of jets and more number of leptons and photons. So it's relatively easier to detect. So in Jinnouchi group, there was a PhD students dedicated for this analysis for the round 1 data. And we are looking into the 3 lepton final states like this, 3 leptons from the W and Z in the decay of the SUJI particles. So the main background is, of course, would be the standard model WZ processes. And here is the result for his thesis. And this is a mass constraint on the neutrino, lightest neutrino mass versus the second lightest SUJI particles. And we could exclude up to 450 GeV. And this was a very early result for the electroweak channel in round 1, when this electroweak channel was not so popular. And then we still continue the similar effort for round 2, and we had another PhD students. Then this time we are looking into the 1 lepton plus 2 photons decay from the Higgs. And the main background was the W and the 2 gamma processes, which was not from the Higgs, so that the distribution would be just flat against the mass of the diphotons. And the other background was the standard model Higgs itself. And this is the 2 plots showing the signal region of these diphoton mass distributions. And the colored histograms is the background expectation, and the data points are showing with points. Then expected signal is this dashed line. And there were mild excess seen in these 2 signal regions with order of 1.5 to 2 sigma. And we had such contribution to the early run 2 data result. But after that, with the full run 2 data analysis, this mild excess was denied. So now looking to the non-conventional signatures. So many dark matter scenarios support the existing of long-lived particles. So long-lived, for instance, Neutrino can decay inside the detectors like this, and then they leave the vertex in the middle of the detector. So Atlas detector is not designed to detect such displaced vertex, so that if with a standard technique, the efficiency of reconstructing such vertex is very low, like this. And this is the reconstruction and this efficiency versus the location of the vertex. And with a new technique, so-called retracking, which we needed to invent, the efficiency is increasing, significantly improves, like these red points, so that we use this technique to for the analysis. So we had the two PhD students, one for the round 1 and one for the round 2 for this channel. And so this such signal should have the displaced vertex with a large mass and also the large number of tracks, so that the signal region of such analysis would be this area. So this colored graph is the simulation for this signal. But from the measurement, actual measurement, the numbers inside these histograms are the data points, data size, and we don't see any events inside the signal region, so that we only set the limit. And we could constrain the greener mass of the 2.3 TeV, which was a very severe constraint. Now we are looking into the next step. So this is the current challenges in a group. So we have plenty of data sets from the round 2, and not all of them are fully digested. So we are now looking to the region where we have not looked into before. Left-hand side is again the electroweak production analysis. These are the excluded regions, but there's a gap in this here, which is we have currently no sensitivities because this area, this detection is very difficult because of the small mass gap between the second and last Suji particles. So because of these small mass ratings, the final state particles are very soft. So it's difficult. Also, because of this small mass difference, this particle could be long-lived. So this makes them difficult to find. Also, this region is just not non-sensitive from the experiment, but this is also sweet spot for the dark matter models. And so we are now looking into this by inventing the new technique to reconstruct this type of events. This is a neutral Suji particle cases, but here, right-hand side is a charged particle case, where we have the similar story. There's a gap in the sensitivities for the chargino decay. And now we are looking into the to reconstruct such event. Now again, this particle could be long-lived, and we expect a displaced vertex with soft pions, but this is very difficult to reconstruct. So now we are investigating this. So summary, TokyoTech physics group are participating in the LHC Atlas experiment. The beyond the standard model of physics is explored. There's still remaining the big questions, dark matter and hierarchy problem, which is a Higgs mass problem, and electroweak symmetry breaking mechanism. So in a group, we are focusing on the Suji electroweak productions and also the unconventional signatures. And currently we are digging into the existing round 2 data sets. And also we are now preparing for the new data taking, which start from 2022. And also, we are now preparing the hardware upgrade for the high luminosity LHC, which I omit from today's talk because we need more time to discuss this. But we have some. I have some backup slides for this. So thank you for your attention.
Okay. Thank you, Professor Osama Jinnochi. It's a nice presentation, overall view of the beyond standard model searches. Now it's the time for questions.
Can I ask two questions? Can you hear me?
Yeah,
Yes.
yeah.
Yeah. Okay. Okay. So thank you for the nice talk. So I just wanted to know what is the prospect for measuring the Higgs coupling to light quarks? Just like you said, Higgs coupling to muons is already done mostly. And the second question was about the disappearing charge track. You said it is difficult to reconstruct if it decays to a soft pion. But is there any measurements like where the disappearing, where the track just leaves the detector? It does not disappear. I mean, can there be any measurements? Yeah.
Okay. Concerning the first question about the Higgs coupling to the, for instance, a charm quark, right?
Yes. Yes.
So let me just go back. So the for the muons, yeah, as you said, it's not confirmed yet, and we need the data from the run 3 to say something more. But for the charm quark, which is more difficult to because of the huge background, so for this, I think we need the high luminosity LHC to declare the discovery. And for your second question about the disappearing track, this. So currently there is a study for the disappearing track. No, not the disappearing track, but the reconstructing the soft pions for the disappearing track search. Yeah, this is currently, I'm not sure if it is published yet or not, but it is such a study ongoing. And it is actually possible, but of course with a low efficiency. And the idea here in our group is that not reconstructing the disappearing track, but we are looking into this short-ranged decay. And because this region is the expected lifetime is short, so that the target is short lifetime. So for this case, if the decay point is less than 1 centimeter, and we can use the standard reconstruction technique.
Mm-hmm.
So that, and also if we assume that if we measure the displacedness of the small displacedness from the prompt interaction point, then it can be used for the reduction of the backgrounds. And that is the idea. For instance, this paper is discussing about such possibilities.
Okay.
Yeah.
Thank you.
Thank you.
Any further questions? Any questions, please? If not, Professor, I have one quick question. So this is MC Kumar. So do you have any plan for the Higgs self-couplings using the channel of di-Higgs measurement?
Yes, we have the plan for this, especially in the high luminosity LHC. And I think I'm not fully sure about the how much we can achieve, but as I can remember vaguely that even with a high luminosity LHC, I think we cannot fully conclude the
Yes.
couplings, but at least we can say something, just like this muon case in the current situation. We might see something, but we cannot, I think, statistically conclude the even with a high luminosity. but the high luminous LHC will be 10 years from 2027, but usually we will extend it. And the first idea was this 3 autobahn of data sets, data volume, but the current plan is to go up to 4 autobahn.
Okay, thank you then.
Autobahn, yeah.
So if there are no further questions, we will move to the next talk. And before that, let us thank Professor Osama Jinouchi for a nice presentation. Thank you, Professor.
Thank you very much.
So now we will move to our next talk by Mr. Kajal Samanta, who is going to talk on precision calculations for the standard model Delian process at the LHC.
So, see my screen? Hello?
Yeah. Yes. And make it full screen maybe.
Okay.
Yeah.
Right, Kajal, you have 15 minutes.
So, yeah. Hi all, I am Kajal Samanta and I am going to talk about the precision study of the standard model Delian process at the LHC. So these are the outlines of my talk. So at the LHC, Delian process, basically the quark-antiquark annihilation process to give a lepton pair in the final state. So for the neutral Delian case, this is basically same flavor quark annihilation, and for charged Delian case, this is two different flavor quark annihilation process. This process is important from the theory as well as experimental aspect because of this dilepton final state has very clean signal. So because of this process is used to measure the luminosity of the collider and also to calibrate the detector. And this process is used to measure the parton distribution function at the LHC. This parton distribution function gives the underlying structure of the proton. From the theoretical side, this process is important to understand the structure of the perturbation theory series. And also for many BSM searches, this process is very important. So keeping in mind the importance of this process, people try to measure and calculate this process very precisely. So this is the measurement from the CMS collaboration. Left hand side for the invariant mass distribution of the dilepton, left hand side for the dimuon case, and right hand side is for dielectron case. Here we can see there is a very good agreement between theory and experimental result. Though at high invariant mass distribution, there is a large statistical and theoretical uncertainty. And from the theoretical side also, this is calculated precisely. So from the theory calculation, or for the calculation from the theory side, this is the basic formula to calculate the hadronic cross section at the LHC, where the FAFB is the parton distribution function, which is a non-perturbative input. Delta AB is the partonic coefficient function, and tau is the ratio to the invariant mass distribution of the dilepton to the center of mass energy of the hadron, and Z is the q square by S hat, where S hat is the partonic center of mass energy. Now this delta AB can be calculated perturbatively using the quantum correction of the theory, as the strong interaction has the strongest coupling, so it will contribute the dominant part in the correction. So for the if we take the quantum correction of this strong interaction, then the typical diagram will come into the picture as shown here. So one gluon can emit from the initial state colored particle, and there can be a loop correction. If we consider this kind of diagram, then we can write this delta AB partonic coefficient function as a perturbative series with the strong coupling constant alpha s. So far from the theoretical side, most precisely calculated process are for Higgs and Delian. So both cases up to n cube LO order, this theoretical calculation has been done, and we can see the Higgs case, the cross section is 45.18 picobarn with the theoretical uncertainty 0.69%, and the non-perturbative uncertainty, that is the PDF uncertainty, is 3.34%. And for the Delian production also, this is done up to n cube LO result, and the ratio to the third order to the second order result is 0.985 and with theoretical uncertainty 0.54% and the non-perturbative uncertainty 2.20%. So if we see the state of art calculation of the Drellian process, we can see that the next to leading order calculation was done long before, almost 40 years back. After 10 years, NNLO calculation was done. Now, in the absence of the N-cube ALO result, because this is very non-trivial and also we have many diagrams to handle. So in the absence of this complete N-cube ALO result, people also try to improve this result, including other correction like electric correction, threshold resummation, soft virtual calculation, etc. And very recently, in this year, the complete N-cube ALO result is also available. But for the dielectron production case, this is available only for the photon-mediated channel. And for W plus minus production case, the full result is available. In this work, we have calculated the N-cube LO SB plus N-cube LL correction in QCD for the Drellian process as well as the on-cell production of Z and W plus minus case. So, as I mentioned that the Platonic coefficient function can be written as a perturbative series of the strong coupling constant. Here n define the order of the series. So n equal to 1 will give you the leading order, n equal to 0 will give you the leading order, n equal to 1 give you the next to leading order, and so on. Now we can see in this equation that the right hand side is mu r dependent, whereas the left hand side is mu r independent. So if we take the all order Platonic coefficient function, then the complete Platonic coefficient function will be mu r independent. And if we convolute this Platonic coefficient function with the all order PDF, we should have the scale independent result. But unfortunately, so far we don't have no technology to compute the all order Platonic coefficient function, and also we don't have all order Platon distribution function. Therefore, the result will depend on these two scale mu r and mu f. So, but the inclusion of the more and more higher order terms in the in the series will reduce the scale uncertainty and also give a precise result of the theory. Now, if you see the structural dependence of this Platonic coefficient function, we can see it consists of three kinds of function: delta 1 minus z, distribution function curly d, and some regular function of z. Now, this is the expression for this curly d, and this regular function is always finite at z tends to 1 limit, which is the threshold limit. Now, this curly d will give a large contribution when z tends to 1 limit. So, this I can take 0 to 2n minus 1 value for a particular order n. For example, n equal to 1, I can take 1 to 0, where 1 corresponding to the leading log, 0 corresponding to the next to leading log. Similarly, for n equal to 2, I equal to 3 is corresponding to the leading log, I equal to 2 next to leading log, and so on. Now, to have a reliable prediction at the high invariant mass distribution, we have to add all these kind of logs. So if, for example, if we add this all red color series up to n equal to infinity limit, then we will have leading log resummation. If we take this pink series up to n tends to infinity, then we will have next to leading log resummation. Now, this kind of resummation is done in the Mellin space, where the typical convolution becomes a simple product, and also at z tends to 1 limit in the G space becomes n tends to infinity limit in n space. In n space, the all order resum Platonic coefficient function can be written in this way, where Gn is completely contain all independent part and G0 contain all independent part. Now Gn, the expression for Gn is given here. If we take the first term in Gn, it will give you leading log resummation. If we take up to second term, it will give you next to leading log resummation, and so on. And if we see the functional structure for the G0 can again written as a series expansion of alpha s, that is the strong coupling constant, and it contains the term coming from the form factor, delta 1 minus z coefficient coming from the soft radiation, and the Euler gamma function, which is the artifact of the dimensional regularization. Now, depending how we are treating this G0 coefficient, depending on these things, there are various prescription of the resummation. For example, if we keep all those terms like form factor, delta 1 minus z in G0 and Gn contain only independent part, then it will give the conventional n bar n exponentiation. Now one can also remove this gamma function from G0 and can keep it in the Gn, and can define a new variable n bar instead of n, where n bar equal to n into exponential gamma e. Then we will have n bar exponentiation. In case of soft exponentiation, one can take out the delta 1 minus z coefficient coming from the soft radiation as well as this gamma e in the Gn in Gn, and then this will give you the soft exponentiation. This can be done because the soft function is always universal, and other possibilities is all exponentiation where the complete G0 is exponentiated and keep in the Gn. So this can be done because the soft function and the form factor both follows the same kind of Kg equation, and we can treat them equally. So we have studied the numerical impact of all those prescription, and these are the numerical parameters we have used for this analysis, and these are the reference of this numerical result. So first we compare the two prescription n and n bar, and here we can see the spacing between lower order and higher order is much closer for the n bar case compared to the n exponentiation case. So therefore, the convergence of the n bar exponentiation is better compared to the n exponentiation. In terms of number, we can see that for n exponentiation, NLO plus NLL give 21.6% enhancement compared to the leading order, and NNLO plus NNLL give 2.2% enhancement compared to the leading order, whereas n bar exponentiation gives 6.7% and 2.3%. So from here we conclude that the n bar exponentiation is a standard exponentiation, and next we will compare the other two prescription with respect to this n bar prescription. So here we compare this soft and all exponentiation with respect to this n bar exponentiation in terms of ratio. Here we can see that at lower order there is much difference between different prescription, but if we go to the higher order, they are becomes very close to each other. And also for the all exponentiation case, we observe that the enhancement is better compared to the soft exponentiation case. Next, we compare these all four prescription by the in terms of the k factor, where k factor is defined in this equation, that is the resum result divided by leading order result. This is simply to show the enhancement in the resum result compared to the leading order result. Here also we observe that the convergence for the all exponentiation is better than other exponentiation. Next, we estimated the theoretical uncertainty coming in our numerical analysis. For that, we follow the conventional 7-point scale variation, where we vary mu r and mu f from q by 2 to 2q, keeping the constant that the ratio of two unphysical scale is always less than 2. And we can see that there is a significant reduction in the scale uncertainty if we go from higher order to lower order to higher order for all prescription. For example, at q equal to 1.5 TeV for n bar case, this leading order LO plus LL will give you 7.61% uncertainty, whereas the final order, that is n cube LO SB plus n cube LL, give only 0.4% uncertainty. And here also we observe that the all exponentiation has a better scale reduction compared to the other prescription. Apart from the scale uncertainty, we also estimated the uncertainty coming from the non-perturbative input, that is from the Parton distribution function. For this, we choose 5 different PDF set: ABMP, CT14, MMHT, PDF, NNPDF, and PDF for LHC, and we compute the uncertainty using the LHA PDF subroutine. And here we see that for CT14, this uncertainty is 16.99%, PDF for LHC is 7.49%, MMHT is 6.17%, ABMP is 6.14%, and NNPDF is 4.21% at Q equal to 1.5 TeV. And we also observe for the theoretical case, this uncertainty is become for NNLO plus NNLL case is 0.54%, and NQLOSB plus N3LL case, this is 0.4%. And the non-perturbative, at this order, non-perturbative uncertainty is more greater than the perturbative uncertainty. Next, we give the result for the on-cell production of the on-cell Drellian production. So here we can see there is a significant, there is an enhancement in the cross section from lower order to higher order, and for G boson case, we can also observe the enhancement in reduction in the scale uncertainty. Whereas for W plus minus case, there is an increment in the scale uncertainty. This is because of the unavailability of the third order PDF, and also the missing regular pieces, which we have not used in our numerical analysis because of the unavailability of the analytical expression of this result. So in conclusion, we can say that we have studied the Drellian production on cell as well as off cell Drellian production up to N3 below SP plus N3 LL accuracy in QCD. And we have studied the numerical impact of different resummation prescription. We have found at Q equal to 1.5 TeV, there is a minus 1% enhancement in the cross section and 0.5% scale uncertainty for the neutral Drellian production. We also observe that more and more term, if we exponentiate, we will have better perturbative convergence, also a better reduction in the theoretical scale uncertainty. We also observe here that at this order, the missing regular pieces, mainly for the Z boson and the interference of Z boson and photon, and the missing third order PDF is also very important. Thank you.
Okay, Kazal, thank you very much for the nice presentation. Now it's time for questions. Questions, please.
May I ask?
Yeah, please.
Could you remind me
Yes.
how you estimate the scale uncertainty?
This scale uncertainty we are using, like we are varying the renormalization scale and factorization scale from 2q to q by 2, and then we are calculating this uncertainty, like this band maximum and minimum, what could be the maximum value and what could be the minimum value, and then taking the separation and then calculating the percentage uncertainty.
Okay, so it's a standard method of changing scales by.
Yeah, this is basically standard one.
Thank you.
Yes.
Hi, may I ask?
Yeah, please.
Yes, sir.
Thanks for the very the comprehensive study results. I'd like to ask you. I think that was page 7 or something. Of the delta AV. Could you go to page 7?
Yeah, yeah.
Okay. Yes. So you mentioned that this equation, you have the renormalization scale only on right-hand side of the equation, and how it is understood. I mean, why this with the summation, why this mu r is disappeared on the left-hand side.
Okay, so this is basically from the renormalization. If you use the Parton distribution function up to all order, it will obviously give you mu r dependent result because you are truncating the series at a particular order, and if you convolute it with the that order strong coupling constant from the renormalization equation, we can see that this scale dependence automatically cancel.
Okay, and so this second equation have the mu r dependence because it's just only the nth order.
Yes, because we are truncating the series.
Okay, okay, great. Thank you very much.
Any further question?
Yeah, Kajol, I have a very naive question. Can you hear me?
Yes, sir.
Yeah. So this difference between NN LO and say N cube LO, so this cross-section differences that you are getting, so that the present LSC can actually have that much of sensitivity, or in the high luminosity only that much sensitivity will be there?
Okay, so this enhancement, I don't know exactly LHC at this moment. LHC can probe this kind of uncertainty or enhancement or not, but okay.
Okay, yeah, that's fine. Yeah, it's just
Yeah, just
Because this process is very important. The hello.
sorry.
continue, Kazi.
Yeah, this process is very important for the many cases. So people trying to calculate it very precisely. Though at high invariant mass distribution, we don't have precise result from the theoretical side because of this statistical large statistical uncertainty. But I think for the high luminosity LHC, this statistical uncertainty can be reduced, and for that case, this result may be important.
Okay. Okay. Thanks.
Okay, then, if there are no further questions, let us close this session 4, and then we'll take a break for 10 minutes. And before that, let us thank Mr. Kajal Samanta for this nice presentation. And we will meet sharp at 10 a.m. according to IST. Yeah. Thank you.
Yeah, and Professor Kuze will be the chairperson for the next session.
Yes, we will resume in Japanese time 1:30
Yeah, sure. Thank you.
in 9 minutes. So the speakers in the next session could test your slide sharing if you like.
Yeah, Debabrat, are you there? Debabrat is the speaker for next session. Or maybe he will come at sharp 10. It's okay. Yeah.
Also, other speakers, Professor Chakraborty and Mr. Izumiyama, also you can test sharing in this break time.
Mm-hmm.
Hi, yeah, this is Osamu Jinuchi. I uploaded my slides before the session, but as I see the website is still not visible, available. Is it something that I need to do on top of?
I mean, your upload was successful, right?
Yeah.
Yeah. No, actually, it does not get uploaded in the site. I mean, in the conference web page automatically. It has to be done manually. So I will, yeah. So I'll ask the technician to actually upload it in our conference web page. Yeah.
Okay. Thank you. Yeah.
Okay. Thank you.
Devashish, Shantu here.
Yes, please.
So, although I have no presentation today, can I
Yeah.
check my slides just by sharing for a moment?
Now?
Yes, because I'm using a different machine. I'm not very sure whether it
Okay.
is.
I mean, yeah. In
If,
1 minute,
if everybody, if everybody is done, maybe I can do it.
Yeah, I do not see anybody trying. I mean,
Okay,
testing.
maybe then.
Yeah, just for 1 minute, you can maybe.
And not even 1
Yeah,
minute.
yeah. Sure.
It's 30 seconds, maybe even less.
Yeah, it's coming perfectly.
It's
no
coming,
problem.
no? Okay.
Yeah.
Thanks a lot. Okay,
Yeah,
thanks
just
a lot.
perfect.
But now I'm
Okay.
using
Yeah.
Mac, so okay.
I see. Okay. Thanks.
This is for tomorrow's talk.
Yes.
Very good. Yes.
Right.
Okay, we can slowly prepare for the next session. I'm the chair, Masahiro Kuze from TokyoTech.
Hello. Yeah.
Yes, next speaker, Mr. Devarat Mahanta. Can you share the screen?
Yeah. Can you hear me, Professor Kuze?
Yes, I hear you. Yes, very well.
Yeah.
And
Thank
now
you.
I also see your face. Very good.
Yeah. Let me do the screen sharing. Okay. Can you see the screen?
Yes.
Okay.
Yes.
Okay. Okay. Just wait a second. Yeah.
Yeah, now it's on full screen. So yeah, we have about half a minute before the scheduled time.
Okay.
So maybe I can already introduce this session 5 is physics of neutrinos and dark matter. Yeah, and the first talk will be by Mr. Mahanta, low-scale leptogenesis and dark matter with observable data and effective at CMB. So please go ahead, 15 plus 5 minutes.
Yeah. Thank you. Thank you, Professor. Okay, so myself, Devarat Mohanta. So I am going to present today one of our ongoing work with my PhD supervisor, Devasis Bora. And let me thank the organizers at this moment for providing me the opportunity to talk in this symposium. And this is the brief outline of my talk. And yeah, let's begin. So, as you know, so there has been these long-lasting problems from cosmological observation and also from the observation of neutron oscillation experiment, problems like the matter-antimatter asymmetry in the universe. And then there is this problem of origin of tiny neutrino mass and the nature of neutrinos, whether neutrinos are Dirac or they are Majorana. And we still don't know the proper answers to these questions, and also the existence of this non-luminous dark matter, which basically constitutes at most of the structures in the universe, and we do not yet understand the particle nature and their interactions. So in this work, we try to address these issues, and actually we try to make a unified framework where we can explain the baryon asymmetry universe to the dark matter, and it can be observed in the upcoming CMB cosmological observations. Okay. So yeah, before proceeding, let me just review a bit about creating the matter-antimatter asymmetry through leptogenesis. So this leptogenesis framework has been very motivating because it connects the high energy baryon asymmetry of the universe to the low scale neutrino oscillation phenomena. And the typical way to do it is considering this Lagrangian, which was proposed by Fukugita and Yanagita. And there one introduces this Majorana fermion, and after the electroweak symmetry breaking, you get a Dirac mass term from this, and you get a Majorana mass term. And after diagonalizing, you get the required neutrino masses. And basically, finally, what you get is you get two kind of neutrinos. One is Majorana left-handed neutrino, which is light, whose mass is of the order of sub-eV scale, and you get another heavy neutrino, which is very heavy. And that heavy neutrino can decay to this Higgs and lepton. And by this CP violating decays of this heavy neutrino, you generate a B minus L symmetry. And then that B minus L asymmetry can be actually converted into a baryon asymmetry by these Spalaran processes. So this is the typical way that one generates baryogenesis. However, so the experiments like neutrinoless double beta decay, looking for the Majorana nature of neutrino, has not seen any promising signature. Therefore, it is also motivating to look for Dirac neutrino mass models and their possible experimental signatures in the near future. So keeping all in this mind, we propose a model where one can have leptogenesis and one can generate Dirac neutrino masses, and also it can also accommodate the dark matter, and it can be probed in the upcoming CMB experiments. So here we introduced, apart from the standard model gauge interactions, we introduced another U1 B minus L interaction, where these are the charges, and we introduce these new degrees of freedoms, right, like this capital NR, and these are the right-handed neutrino, which will give the Dirac mass to the neutrinos, and another doublet scalar and two singlet scalar to give masses to these fields, to fermion fields. Okay, so this is the minimal setup. However, this is not anomaly free from this. So yeah, this is the minimal model one can have to achieve these three things at one go. Okay, then one can write this Yukawa Lagrangian. As you can see that this term after electroweak symmetry breaking will give you the neutrino mass. And however, this capital R, the decay of capital R to this doublet scalar and the lepton can give you leptogenesis if you have CP violation here. And you have two terms where the B minus L asymmetry will get broken. These Majorana fermions will get masses. Yeah, one important thing here is to notice that there is no lepton number violation in this Lagrangian at the order of delta L is equal to 2, which is in general the case in the conventional leptogenesis scenarios. But here we violated lepton number by unit of 3 once this B minus L asymmetry gets broken. And keeping all the symmetry in mind, one can write this following scalar potential. Okay, so then the leptogenesis, the usual kind of decay processes that one has, the tree diagrams and the self-energy and vertex diagram. One need to take the interference of all this tree diagram, and one can find the CP symmetry parameter for this decay is like this. So these Y eta are this new Yukawa coupling, which basically connects to the leptons and doublet. And here you can see that now our CP asymmetry parameter is completely free from the Dirac neutrino Yukawa coupling, which should be of the order of 10 raised to the power minus 11 or less even. Therefore, we have the freedom to tune our Y eta such that we can generate sufficient CP asymmetry. Okay. And the CP asymmetry, apart from the decay, there will be some washout processes which will basically wash out the generated B minus L asymmetry. And there will be many of them if you carefully look at the model. However, we are mainly interested in the washout processes that are basically, that involves the new gauge interaction. And you can see these are the two processes that can be possible, which basically violate lepton number by unit of 1, and then they can erase the generated asymmetry. And you can see here, the process 1 will dominate over process 2 because there is a light mediator in this diagram, and you will see their effect in a few minutes. Okay, so these are the relevant Boltzmann equation one can write. So there will be two Boltzmann equation, one for the decaying fermion and other for the B minus L asymmetry. And these are the different washout processes. We all the processes are taken care in this Boltzmann equation, and one need to solve this equation, and we did it, and these are the results. As you have already seen that there are some gauge involved washout processes. Therefore, you can see if I increase the coupling of the gauge bosons, so basically what happens, the asymmetry decreases purely because of increasing the washouts. Similarly, if I increase the mass of the gauge boson, then what happens, you see that also if I increase the mass of the gauge boson, the asymmetry decreases because of increasing gauge boson, because this channel dominates, and as I increase JBL, this cross section basically increases. Therefore, you get a decrease in final asymmetry. And these are the plots that we made for the final asymmetry, eta B, baryon to photon ratio, with the mass of the decaying fermion. So as you can see, if I increase the mass of the decaying fermion, the decay width increases, and therefore the source term for leptogenesis increases. Basically, in the Boltzmann equation, there are two computation between this source term and these washouts. Okay, so if I increase the mass term, mass of the decaying fermion, the decay which increases, and you get an enhancement. However, you can see the behavior for the washouts. If I increase this JBL, I need more and more heavy fermion to generate the correct order of baryon asymmetry. Similarly, for this also, for JBL, MJBL also, you can see the similar effects. Okay, so leptogenesis is done. So let's talk about the dark matter. Here, basically, we have two dark matter candidate. One is this chiral fermion chi, and another is the doublet scalar. However, we are basically interested in this, as you have seen that we need small GBL to generate the correct order of baryon asymmetry. Therefore, for the parameter space of this doublet is already known in the literature, and it is always suppressed in this mass range. And in addition, it has now JBL interaction, therefore it will be even more suppressed. And with small GBL, this chi will be overabundance because this cross section will be small enough, and therefore if you add this relic for this, you will make the things even worse. That's why we put this doublet to be its desert region where it is always under abundant, and we look for the relic for this chi field. Okay, and though this dark matter chi can have scalar interaction, but here we were mainly focusing on the fact that we want to basically constrain the B minus L model from different experiments. Therefore, we are only focusing on the channels that are mediated by the gauge boson, and we are making the singlet scalar to be very heavy compared to the mass of the dark matter. And this is the usual Boltzmann equation for the dark matter. Okay. So yeah, these are the results for the dark matter. These are the expected results for MJBL. This is the resonant effect that you can see. And yeah, so and similarly, if I decrease this GBL, I get overabundant of this. So see how it is overabundant because of small values of GBL. Okay. And finally, what we did, and here we have taken these scalars to be very heavy such that there is no scalar mediated interaction involving in the relic. And yeah, let's go to the detection part. I mean, in this model, we have Dirac neutrinos and how they can be detected in the near future cosmological observations. So yeah, the effective number of degrees of freedom at the time of recombination, the Planck measured value is this. However, the standard model predicted value of n effective should be this. And you see that this is perfectly consistent with the experimental observation. However, one still has a window to accommodate new physics here. I mean, new physics in the sense, if some light degrees of freedoms were there in the thermal equilibrium, they can contribute to these relativistic degrees of freedom, and CMB can be sensitive to this. So in this type of scenario, the effective contribution from the right-handed neutrinos to the n effective. So if I put some right-handed neutrino in the framework, and how much it can contribute is given by this, the change in n effective basically. And these are basically the generations of right-handed neutrino you are introducing, and these are the temperatures of decoupling for the right-handed and left-handed kind of neutrinos, and G is basically the relativistic degrees of freedom at that epoch. And here, this you know from your model, and this we already know at what epoch the left-handed neutrino decouple from the thermal plasma. And we need to know this T nu R, and that can be actually found from this equation when the interaction rate of this right-handed neutrino basically starts, basically the Hubble starts dominating over the interaction rate, then they decouple from the thermal plasma. So here all the model parameters are there, okay, in the decay width. So you can constrain your model from observing delta n effective. And the upcoming CMB stage 4 experiments will have the potential to constrain delta n effective up to a very accurate precautions. Therefore, accuracy. Therefore, N effective can be measured up to this 0.06 with 95% confidence. So this can be a very general probe for this kind of model. And here finally we have done a summary plot for these new interactions. So you can see these red bands and these violet bands basically represents the points which can give you the correct order of asymmetry for these different values of decaying particle, mass of the decaying particle. And these blue points can give you the correct dark matter relic. However, we already has the existing bounds, like bounds from the LHC and bound from LEP. We already have this, and bound from Planck 2018 data. And here you can see as I am increasing the MJBL, I need smaller and smaller JBL to have successful baryogenesis. And the case is the reverse for the dark matter, as we are mainly focusing on the B minus L mediated channels. Okay. And you see there are still some points that can survive from these existing bounds. However, the upcoming experiment like this South Pole Telescope 3rd generation and CMB stage 4 experiments can actually has the potential to either rule out or get some points here. Okay, because they have very high sensitivity to delta and effective, and they are going to test these kind of models with very much accuracy. And yeah, at the end, the minimal model that we considered was not anomaly free from the gas sector. So to calculate the anomaly free calculation, one need to consider this full model that we are doing currently. So here we have these two chiral fermion that were required to cancel the anomalies. And basically you need 4 chiral fermions, and the linear combination of them will give you the dark matter candidate. And while we have one additional scalar singlet, and we do not expect the results to differ much because we are sure that the leptogenesis result will be the same as compared to the minimal model. However, we may be able to loosen some constraints from the dark matter parameter space. But still, as we are looking to focus on the points where all these baryon asymmetry and dark matter can be satisfied, we do not expect much deviation from the minimal model. Okay, so finally I am concluding saying that this model is successful in explaining the correct baryon asymmetry and dark matter, and leptogenesis sector is completely decoupled from the tiny neutrino mass generations, and the model can be strictly constrained from all these bounds. And the upcoming future CMB observations will actually they will have the potential to rule out these kind of models with 95% level of accuracy. Yeah, thank you for listening.
Thank you very much for very interesting talk. So questions or comments? Maybe I'll ask. Have you checked the compatibility with the AMS excess of positron?
Sorry?
AMS experiment on the space reported some excess of high energy positrons in the cosmic ray, which could be explained by dark matter annihilation of a few hundred GeV.
Okay.
Does this model match with this claim? Or?
Yeah, actually, dark matter annihilations. I am not sure, but dark matter abundance has always frozen out in this kind of model. Like this is the new gauge interactions that through which dark matter freezes out. So dark matter interaction rate has already fallen over the expansion rate of the universe at the very early epoch. So yeah, I have to look into that, but I guess that is not the case here.
Mm-hmm. Okay, thank you very much.
Yeah.
Any comments or questions from the audience? I don't seem to see, so it was very clear.
Yeah, fine.
Okay.
Okay, thank you.
Thank you very much. Let's thank the speaker again.
Yeah.
Okay, so we move to the next talk of this session by Professor Chakraborty. So
Yeah, can you hear me?
Yes, I can hear you.
Yeah. Okay, thank you.
Try
So I'm going to share my screen.
share, yes. And if you can, also we welcome to see your face while you are talking.
Yeah, but I mean, I see my video is, I mean, my camera is not being recognized by Zoom.
Ah,
so
that's
yeah,
okay.
but in my slides you will have my picture. So
very good. Please,
So, Shobhan, before you start, can
Yes.
I ask you a question?
Yes.
I heard that there is a about 3 weeks lockdown announced in Munich.
Yes. So
Complete
yeah,
lockdown.
yeah. It's like complete lockdown in Munich. Yes.
Ah, you're in Munich.
Yes. It's pretty early in the morning, and I'm scared that my daughter will wake up. But let's hope it doesn't happen.
Yes. So
Yeah.
the talk is
Yeah.
Supernova neutrinos, oscillation, and phenomenology. Thank you very much. So
Yes. Yeah.
please
Thank you.
start.
But you can see my screen, right?
Yes, with
Yeah.
the thumbnails on the left, but that's also okay.
Is it full screen now?
Not yet.
Okay. Okay. I think the PowerPoint might have some problem. Let me go to the PDF. Sorry. Yeah, just a minute.
Now we see the PDF.
Yeah, is it full screen now?
We are waiting, it seems. We see only black screen now.
Oh, is it black still now? Sorry.
Yeah, maybe it goes well enough with without the full screen mode.
Yeah. Okay. It's fine. I think it's fine with this one, right?
So yeah, okay. Please 25 plus.
Yes. Yeah. Okay. So we are going to talk about supernova neutrinos, oscillation, and phenomenology, and this is my group. So yeah, so here I am, Shobhan, and we are mostly working on like high energy physics, gravity, astrocosmology in the borderline of all these areas, and we have like 3 research scholars in our group. And the talk I'm going to give is mostly dependent, I mean, on Madhurima Chakraborty's work. And okay, so just for preliminaries, because I see a lot of students in the audience. So basically, neutrinos, if you know, like are the most important building blocks in the standard model. There are like 3 kinds of neutrinos: electron, muons, and towns, and they are actually chargeless and weakly interacting. So that actually makes them an excellent astronomical messenger, because now they can actually travel from far away without interacting with anyone, without getting deviated from the different magnetic fields on the way. So neutrinos are like excellent astronomical messengers, and also they're almost massless. You heard the talk from Devabrut Brihad before, and though they are almost massless, they are not actually massless. They are tiny masses, and that actually tells that neutrinos can actually oscillate. And we know in 2015, Professor Kajita and McDonald was given the Nobel Prize for discovering that neutrino oscillations are there. So this is like a background for the neutrinos. And then we know like there are like different kind of sources of neutrinos, and one of the most abundant sources, and though they are rare, very rare, but like one of the most luminous in neutrinos would be a supernova. So what are the typical problems in supernova neutrinos? So first we have this production, like, so you can see like the neutrinos will be produced very close to the supernova core. And then these neutrinos will start traveling outside. Once they're traveling outside, they will travel through the star, and you can have these different kind of neutrino oscillations. We'll soon see what are these neutrino oscillations. So neutrinos of one flavor can actually move to another flavor. And then while they actually finally detect at Earth, and you have to detect them. So basically there are three phases of this supernova neutrino problem. One, how to produce them, then how do they propagate through the star, and in fact when they reach Earth, they can also propagate through the Earth if your detector is on the other side of the Earth. So there are like detection problems, or like different kind of possibilities of detection. This is what you call phenomenology. And this middle part is the oscillation part. And this talk mostly will be focusing on this oscillation part, on the propagation part. There is another talk after mine which will be talking about this neutrino detection. So I will be just doing very briefly towards the end. I will talk about some phenomenology. And there is this nice review which is written by us, like with colleagues from all these different areas, from production, propagation, and detection. And it's also very well written. So I mean, if you are interested in this whole problem, please go and see the review. And so okay, but very briefly, let us remind us about the neutrino production. What is this neutrino production? So how does this core collapse supernova happen? So basically you have this very large star, more than at least say like 8 times solar mass, and it's actually fuel, all the fuel is being burned by the nuclear reaction and the gravitational collapse happening. At the end of the stage, you have this onion ring like structure where you have this very heavy the heavy iron at the center, and as you go outside you have the lighter elements. And this iron core at some point will start collapsing due to its own gravity. And then finally, this collapsing core will reach a nuclear density. So now you cannot compress anything beyond this extreme density. So what will happen, as it starts collapsing, there will be a shock wave, and the shock wave generated star will actually burst. And when this shock wave actually disintegrate this iron core, you will have these neutrinos coming out of this star, and these neutrinos will actually take almost 99% of the energy of this collapsing star. And what you have is this newborn neutron star. And but what do you know about these neutrinos which are coming from the star? That they would be of their energies of the order of 10 MeVs, and this neutrino emission will actually take place only about 10 seconds. And this is kind of very basic prediction from this model. There can be from this kind of a core collapse mechanism. And indeed we saw something like that in 1987 when this star, this Andaluk 69202 in large magellanic cloud actually burst, and we have this very famous supernova 1987A. You can see the star here just before the burst, and you can see the star after the burst. You can see the whole galaxy is basically luminous. I mean, only this environment of the star is luminous from this burst of the supernova. And that happened 23rd February 1987. And exactly at that time, in Earth, we saw about 20 events at around 10 MeV, and these events were spread over about 10 seconds. So this basic prediction was kind of correct. But then when you try to redo this whole thing in simulations, you really try to recreate these events, there are problems. They actually does not work. There are several problems. So to just to label them. So the first problem you have like small mass stars. For a small mass stars, this mechanism I described kind of works pretty fine. But as you go to stars which are like more than 10 solar mass, this shock, when it is actually traveling from this iron core, it loses energy because it's actually disintegrating this iron, and then this shock actually stalled. It cannot go out and cannot burst and throw out the whole supernova. So, I mean, this is the basics in the problem, the biggest problem in any kind of supernova simulation. But what people have been seeing is like more or less like for a broad mass range in 2D, basically if you have only axial symmetry, then this kind of simulations for even for larger mass things are happening. But your actual problem is not a 2D problem. It's actually the axial symmetry should not be there. So in 3D, basically you're having mostly failed simulations. So what is the different possibilities people are thinking? So one of the most popular one from the very long back is something called the neutrino heating. What is this neutrino heating? Here you can see the protoneutron star and this neutrino sphere. Basically, neutrinos are actually this kind of the last scattering surface of the neutrinos. Neutrinos are emitting from here, and here in the red you can see the stall shock. So the neutrinos which are coming from inside will actually dump some part of their energy behind the stall shock, and this can actually revitalize or like rejuvenate the shock. This is called the neutrino heating mechanism. And this neutrino heating mechanism can actually become much more efficient if you have neutrino oscillations. What do I mean? You see, like here in this slide, I actually show you the spectra of the neutrinos. So you can see the energy. You can see the electron neutrinos have the lowest energies, and the X basically means the nu mu nu tau, the heavy lepton neutrinos. They have the largest average energies. Now, if you somehow you can actually oscillate these fluxes. Basically, if the nu you can take the energy budget of the nu mu and nu tau, it will have like more efficient neutrino heating, because nu e is or nu e bar, they are actually more interactive because I mean they have like both the charge current interaction for nu e, and you will have like much better efficient neutrino heating mechanism. So this is like one possibility people have thought of. And then let us very quickly see, since we are talking about neutrino propagation, what happens to neutrino propagation. Now, to neutrino propagation, this neutrino propagation inside the supernova is actually very, very different than sorry, can you see the slide still?
Yes.
Yeah, okay.
Yes.
Yeah, it just went. Yeah, okay, fine. Yeah. Okay. So for the supernovae, the neutrino oscillations are really very different than our normal environment, like what happens for neutrinos inside a star. Here you can see, like for a normal vacuum or MSW kind of flavor conversion, for a given momentum, and which of course requires neutrino mass, what will happen, like the nu e goes to nu mu. And this kind of oscillation is driven by what you call like the frequency, or this oscillation is driven by like this delta m square by twice c, some factor, and this thing actually comes of the order of like a kilometer inverse for a typical supernova neutrino energy. However, inside the supernovae, what would happen is like now your neutrinos will actually interact with other neutrinos. You usually do not take this kind of interaction because neutrinos are definitely weakly interacting, but the neutrino densities are so large that that inside a star or even something like an early universe, these interactions actually becomes important. And when you look into this kind of interaction, these interactions actually make this whole thing go like something called a collective effect, because neutrinos of different energies now become somehow coupled. And what has been shown that this can actually happen actually even at a vanishing mass square difference or vanishing masses. Why? Because this is actually driven by a different frequency, and the frequency is actually the density of the neutrinos. So this is called the first collective effect frequency, if I call them. And you can see for a typical supernova neutrino environment, this number is almost 5 orders smaller than the typical vacuum square vacuum frequency. It's something of the order of centimeter inverse. And this was actually shown by us, and this was very I mean, this work was actually published in the special issue, which was celebrating the Nobel Prize in 2015, and that was actually for talking about oscillations, which depends on neutrino masses. And there we first proposed this idea that this kind of oscillations can happen even for vanishing mass square difference. But this actually does not happen. Neutrinos have masses, and this is not the point. But the point is that mass actually becomes unimportant for this kind of scenarios. So now let us see a bit more what actually is happening Now you have these. This is a schematic diagram. What is happening? This is your neutrino sphere, very inside the star where the neutrinos are being emitted, and here you have all these exotic interactions happening. Further away from this neutrino sphere, you will have your usual MSW region, which is happening at the time of some 10 to the power 4, 10 to the power 5 kilometer. And this kind of extreme oscillations I'm talking about happens within, say, like 100 kilometers. And this fast oscillations, what I talked, happens even within like some tens of kilometers from the neutrino sphere. Now let us see, like, basically some mathematical structure how this actually happens. So this is the neutrino transport equation for a supernova like scenario. You have this neutrino gas. It follows a Liouville like equation, and these rows are the matrix of densities. And this rows, this is kind of this occupation number matrices. Your diagonal elements gives you the total flavor content. As we know that the off diagonal elements will tell you if there is a flavor conversion or not. So to begin with, your off diagonal elements are 0. If there is a flavor conversion, they becomes non-zero, becomes of the order of the diagonal elements. And then you will say, okay, I can have some kind of flavor oscillations. Now, if you look into this evolution equation, it's actually a pretty difficult one because it's actually a 7-dimensional problem. So you have a 7-dimensional partial differential equation to solve, because one comes from time. We have 3, which comes from the spatial evolution, and this what you call momenta is basically comes from the emission geometry. This is in a way like very smart way of saying it, a momenta, but actually what happens is basically this is another set of parameters which comes from the emission geometry of the supernova. So now this problem, as you can see, like itself, it was pretty difficult. Now if you look at this Hamiltonian in this Liouville equation, it actually has this usual mass square mixing, this lepton densities. But this third term, you can see this rho is again sitting here. So basically your problem is now nonlinear. So you have a 7-dimensional nonlinear problem to solve, and they're like, and you can understand this integration is actually over all the different energies and different angular modes, because you can have neutrinos emitting at different angles. So when you have this all these different modes, this is actually a very difficult coupled nonlinear partial differential equation, the most difficult kind of equations you can think of solving. But I mean, now solving is a different part, but now you understood something already here, that these different energy modes and different angular modes gets coupled because of this integration. So that would actually make that the different energies and angular modes actually oscillate together because of this, and which will come from the strength of this interaction term. This can be seen very nicely here, that you have this say, to begin with, you have this electron and this nu x. Basically nu x, I already told you, this nu mu and nu tau, and they are spectras at the neutrinosphere to begin with. And once you have the collective effect, you can see, especially at the antineutrino, you can see there is a swap between this black and this red line. Basically what happened, your electron and this X flavor has completely swapped their flavors. And this has happened for all energies, unlike the normal vacuum or MSW oscillations, which happens at some typical energy. For some particular energy, this is happening for all energies. The reason is because all your energy modes are already coupled. Now, this is a very typical example this is example for a very simplified scenario. But this is like a easy way to understand what can happen actually. Now the real problem is definitely much more difficult, and here is the one explanation what happened, why they actually become independent of the masses. Now when you look into this, this kind of oscillation can become independent of the masses. The reason is that in this calculation, actually what goes in is something called a spectrum. Spectrum is basically, as you can see, the flux difference between different neutrino flavors. And this different neutrino flavor flux difference can itself be actually dependent on the, not only on the energy, but the emission angles. Like here, which is written as momentum, is basically means this different emission geometry, this theta and phi. Now, what we actually propose that if you have this G, usually what people are doing, they are looking into this G, which is only dependent on the energy. But if you actually take this G to depend on these angles as well, so basically different angular geometry or these angular differences, the problem can actually make this very unusual kind of solutions where you can get, where you have these oscillations happening very fast and even independent of the masses. So here is again another schematic way of understanding that. Say these neutrinos were actually emitting from here, and these neutrinos of different flavors have different interaction, and they can actually leave this star. They are not going to leave the star exactly at the same radius because they have different kind of interaction. Here you can see the green is basically your mu and taus, this nu x what we are calling, they will leave most far at first. Then we'll leave these red ones, what is basically the electron antineutrino types, and at the end the electron neutrinos will leave because their cross sections are larger. And now you can understand, if you're sitting farther away from this thing, the angular distribution of the ones which is leaving earlier will actually become more forward peak to you. So the angular distribution will not be same if you're sitting some point here in the z. And this is the reason, this is angular distribution difference, which actually finally boils down to this very unusual kind of oscillation, which is actually being shown here, like these different probabilities for different kind of parameters, which you do not need to go into, but you have these oscillations. And the two requirements for this kind of oscillations were the electron antineutrinos are contained in a narrower forward cone, and the more electron antineutrinos than the electron neutrinos. This is like two kinds of requirement you should have, and if you have that, your flavor conversion becomes independent of masses. An extreme rate of conversion can happen. That is the fast oscillation. And this actually has now I mean, this proposal has actually now become very popular, and there are a large number of papers written even in this very small area of field. Almost 60-70 papers has been written in last couple of years, and the papers are mostly looking into the different neutrino production characteristic of supernova models, and of course oscillation studies without different approximations people are trying to understand, and what are the possible phenomenologies. In this regard, you can actually look into this very interesting paper by the collaborators of Yamada et al, Shiochi Yamada. And here you can see what they are showing here. Here you can see in orange this neutrino density. I mean, sorry, the electron density, or basically the shock profile. You can see here this very sharp discontinuity. And in this red or this black and these dotted lines are showing you the growth rate of this kind of fast oscillation. You can clearly see just behind the shock, these fast oscillations have started happening. So in a way, you can see the title of this paper: possibility of fast neutrino flavor conversion in the pre-shock region of core collapse supernova. So these shocks can happen behind the shock, and this kind of things can actually completely change the way we are looking at the supernova problems. But then, even in this paper, all the 60-70 papers I mentioned, they never took into the point that neutrino emission from supernova are actually not of two neutrinos. They are actually three flavor problem. And this is something we did recently. So this was like, already before that, we are actually looking into this three flavor picture. And of course, this three flavor picture was much complex, and it has a much complex dependence on these different fluxes. But then why should you do this three flavor problem? Because people usually what you take is this kind of a scenario, that the neutrino and antineutrino have the electron type has some difference, but the muon and the mu bar does not have any difference. If you can see, if their angular spectra is exactly similar, say let's look into the first equation, you can see that's mu and mu bar, if they have same, they will actually cancel, and everything depends only on the electrons. Fine. So if this is something happening, then why should you actually take a three flavor scenario? The reason was, if you take a three flavor scenario, only when such kind of things are happening, that mu and mu bar has some kind of difference. This was encouraged by this very famous paper in PRL by Thomas Yanka and collaborators, where they actually showed that this supernova environment is actually hot enough to create muons. If you can create muons in the supernova scenario, then you can actually have this asymmetry between muon neutrinos and muon antineutrinos. And here you can see these red lines. At least here you can see the fluxes. Let's look into this one. You can see these red lines are for muon neutrinos and anti-muon neutrinos. You can see there is a large difference, and the black lines are if you do not take this muon production. So this actually encouraged us to look into the scenario if you actually not only take this electron lepton number, but the muon and the tau lepton number as well. So this has been recently done by my collaborators and my student, and this is also appearing in PRL. And here you can see the problem, say like this blue one is actually what we are showing is this off-diagonal elements growth in time. You can see that extremely very fast in nanosecond time, these things will actually grow. Basically in centimeter length order, this kind of oscillations can happen. And for a two flavor one, you can see there's a large growth in this. This is dotted one for the two flavor case. But if you take a three flavor case, you can see there is no growth in this blue and this green line. So this is like one case we showed. There's another case where you can show that this two flavor case, you have only one kind of growth. But if you take a three flavor, then all different kind of oscillations can happen, and you can have a quantitative difference. So I mean, in all these examples, which were actually inspired by this muon simulations, we actually showed that a two flavor analysis of fast conversion is actually not complete. One needs to do a three flavor one, and a future muon simulations can actually give the correct direction. The present muon simulations do not have enough angular beams to tell us what kind of exactly what kind of angular distributions are there. So this is basically what I had to talk to you about, the oscillation propagation part. Now, if I have some time, I can actually very quickly talk about a bit of the detection one. So the detection one, so now, I mean, you must be worrying like, how do you actually detect these neutrinos and what kind of effects do you see from this kind of oscillation? There are several kinds of possibilities from energy spectra, time spectra, many different things can happen. I might actually talk a bit about this rise time analysis, one or two slides. This is something we are doing for this hyper-Kamiokande collaboration. And but before, let me tell you just briefly, those of you are like students, like how do you actually detect these neutrinos? So these neutrinos are detected mostly by this anti-neutrino capture on proton, and there you create this positron, and these positrons will give you some Cherenkov light, and by photomultipliers you actually detect this light. So this is the most popular and most well-known process. So these are like the anti-neutrino detectors, and these detectors are actually, you can see these different detectors all over the world. So one of them is actually in Antarctica and called the ice cube detector. However, most of these detectors, as I told you, is anti-neutrino detector, but there is a new detector coming in USA, which is the DUNE, and which actually looks into this whole picture, but through neutrinos, not through anti-neutrinos. And IITG's Professor Bipul Bhuiya's group is actually part of this DUNE collaboration. So, okay, so now let me just quickly mention something we're doing for the Super Kamiokande's future collaboration is called the Hyper Kamiokande collaboration, for which we are actually looking into this thing called the rise time analysis. The idea is, like, I will not go into detail. The idea is that, like, in the inverted mass ordering or inverted hierarchy, the fluxes or this of the anti-neutrino fluxes will rise faster than the normal hierarchy one. You can actually see from here. It's actually, this is done for ice cube actually, but for ice cube you can see this inverted hierarchy. The blue one is rising much faster than the normal hierarchy one. The reason is from the oscillation feature it comes that the inverted hierarchy one is completely dependent on mu x. And the normal hierarchy one depends on both the antineutrinos, electron antineutrinos, and mu x. This is really this nu mu's and nu taus. So from oscillation you can expect this kind of a feature. And here you can see, like, we have done some preliminary calculation for a megaton water Cherenkov detector, and there you can see that both these different kind of mass orderings are actually for different models of supernova, for different masses of supernova, are really far away. It's almost 5 sigma away one can actually differ this thing. So this is something. So my group is also part of the Hyper K node of India. So we are doing a megaton water Cherenkov study. We have recently started this study, and hope we will be able to find something very interesting in this one. And also, of course, we are also working on this diffuse supernova neutrino background, which the next talk is about by Mr. Shota Izumiyama. So please listen to that talk. This diffuse supernova neutrino background is a very fascinating idea, and you will learn a lot from there. And okay, so here I am at the end of the talk. So this is like the future outlook. So this is a very interesting picture from the supernova 2016, but it is actually seen in light in even like optical telescope. And here you can see in this first part, you have this blue lines. These are the shock breakout line of that star, which was actually observed for the first time, and that's why this paper came in Nature. So what we have to do is, like, for a supernova group, working in neutrinos, that you have to still wait for such a line from a galaxy, from our galaxy, from Milky Way, and you will have something like that soon from Ice Cube, Super K, or Hyper K collaboration. So just wait for that, and we'll have some very exciting physics coming from our next galactic supernova. Yeah, thank you.
Thank you very much for this very fascinating talk. Questions, comments?
Maybe I
Can
can
you
ask a
repeat?
question. Oh, sorry. Yeah, there's already. Go
Uh,
ahead.
what was the reason for having stars with a solar mass as more than 10 or so? Uh, like you mentioned something about having a difficulty in simulation or so for the neutrinos produced.
Yes, because you have I mean the preliminary simulations were pretty successful from say like 8 to 10 solar mass. So these are like very small stars, and in this kind of stars, there is, like the iron core, most of them, you do not even have. So there is this part of cores, stars which are like about say like 8 to 9 solar mass, where you do not have this iron core problem. But if you, as you go for larger stars, the iron core becomes larger, and then the shock cannot actually break out to that iron core. So that's why you have the problem when you actually go to heavier stars. This is like one problem. There are like several others, but that's the main thing which happens.
Okay, thank you.
And Professor Das is raising hand.
Yeah, Shobon.
Hi.
So basically, the neutrino that you are talking about, they are high energy neutrinos, right?
No. I'm talking about MEV neutrinos. So they are the low
MEV.
energy one. Yes.
But anyway, so the solar neutrinos are even less energy, no?
No, solar neutrinos are like, okay, of course they are below 10 MeV, but like they are also MEV neutrinos in some sense. They are like between like, yeah. So between say like 1 to 10 MeV, we have different solar neutrinos spectra. Okay.
So my question is, why you do not consider solar neutrino as a source instead of supernova? Because solar neutrino are coming from nearby places, and
oh yes, solar neutrino. No, solar neutrino is definitely the source, and from which Professor McDonald, like this whole SNO collaboration, the Nobel Prize came from solar neutrinos, right? So solar neutrino as a source is very fascinating. People are studying it a lot. I think still now SK and Hyper K, all these collaborations, they are pursuing solar neutrinos. And people even try to use the solar neutrinos on the opposite way to even study the solar models. So yeah, solar neutrino is a fascinating source. People are still interested and they are doing these studies. But like the kind of densities you require for neutrinos to interact with other neutrinos can only be achieved inside a collapsing star or in early universe.
So this all about the interaction between the neutrinos. So that is the main physics that you discuss.
Yes. So like in a sense, like this supernovae collapsing core gives you like a small model of basically the early universe. So like exactly like the neutrinos have a last scattering surface, they leave the star, and yeah.
So related to that, my another question is, can you use your analysis for the detection of the neutrino source?
Yes, indeed. That's like sorry. So, that's why it is actually so fascinating, because the neutrinos are actually coming from the deep inside the core. Your electromagnetic radiation cannot give you information from deep inside the core. Okay, maybe 20 years after the supernova burst, you can actually look into the neutron star and can try to understand okay, what happened there. Like, yeah, but like to begin with, at that point, the neutrinos are the only kind of uh, uh, only like still now detectable kind of particles you have, which gives you information from deep inside the supernova core. So yeah, so that is why like this whole supernova mechanism, that is why this 87A was like so fascinating, that like you could really see like this Bethes proposal that supernovas will actually have neutrino emission, could really formalize and you could detect that, I think that must have been extremely exciting. Yeah, I mean, especially for people in Japan, like, because Kamioka was able to detect these neutrinos.
Okay, so I think time is up. So let's thank the speaker again. Thank you very much.
Yes.
Thank you very much for waking up so
Thank
early
you, thank you,
in
thank you.
Germany. Okay, so let's move to the last talk of this session by Mr. Shota Izumiyama. Your face and also your please, Professor Chakraborty, can you turn off your sharing? Yes, thank you.
Okay, now I can share my screen.
Yeah, and please,
Okay.
everybody mute. Professor Das, can you mute? And talk is detection of supernova relic neutrinos with large water Cherenkov detectors. 15 plus 5 minutes, please.
Okay, thanks for the organizing this workshop. I'm Shota Izumiyama of TokyoTech of the Xeria groups. I would like to talk about this supernova relic neutrinos with large water Cherenkov detectors. Let's start. First of all, yeah, I'd like to introduce from the SN1987A. This appeared in the sky about 30 years ago. Like this is the before and after. They shown the results. And yeah, what's the important thing is that we observe some neutrinos from this supernova. We observe about 20 neutrinos and the 3 experiments of the Kamiokan-2 and IMT and Baksan. This left plot shows the scatter plot of the time and energy. This time scale is about 10 seconds. Its energy is about 10 to 50 MeV. And this total energy is released as 10 to 53 eLVs. This is one of the very intense phenomena in universe. And yeah, this Quark supernova is introduced where in the last talk, so I can skip this. But yeah, this is a light plot. It shows the neutrino light curve and the luminosity amount very high, 10 to 53 per second. And yeah, this Kamiokan-2 and IMD experiment is a type of the water Cherenkov detector. This type of detector observes the charged particle with override speed in the water. This is the schematics of the Cherenkov radiation. This is a charged particle. It generates Cherenkov photons as a cone shape. And this experiment detects its photon by the pulse sensor PMT on wall. This is the schematics of the Kamiokan-2 detector. It looks like the cylindrical shape of the diameter about 16 meter and height is also 16 meter. This cylindrical tank is filled with pure water and this amount to the 3 kiloton scale. They are about 1000 PMT with a large aperture of PMT type. Yeah, this Kamiokan-2 aims originally aims photon decay and searching a ground unified theory, and it's found to be that it is very sensitive to MAP neutrinos also. So it's success to observe SN1987A. And now, this Kamiokan is before the 30 years ago, and now this role is taken over by a super Kamiokan. This is the largest underground water Cherenkov detector located in the Kamioka, Japan. Its size is 8 times larger than the Kamiokan. Diameter is 40 meter and height is 40 meter. Target volume is 22 kilotons, and this is pictures. And yeah, since the package is very large and the number of PMT increased to the 11,000, and it started its operation from the 1996. This is the same age of me, and this continues its operation today. The advantage of this water Cherenkov detector is we can build large volume since the water has a high transparency. And another advantage is its energy threshold. We can reach 5 MeV in about 5 MeV. And this is an overview of the supernova relic neutrino. The super K has a large volume. However, its reach of the supernova burst detection is about 100 kiloparsec. Comparing to our Milky Way, distance to the center is about 10 kiloparsec, and this is not enough to see the other galaxies. And CCSN rate in this Milky Way are only once in centuries. This is very rare event, and we may miss these rare events. However, once we see the whole universe and the CCNS rate amount to the 1 per second, and these burst neutrinos are diffused in the space around this large universe, and this can be detected and called as supernova relic neutrinos or diffuse supernova neutrino background. Since these diffuse super SRN signals are continuous and diffuse, so this is signal are guaranteed to be detected. This is the spectrum of the SRN. This is the flux. It consists of the 3 terms. First is the cosmic time evolutions, and second term is the RCCSN, is the CCSN rate at the redshift J. This is determined from the star formation rate, and this star formation rate there are unsolved problem for the failed supernova rate. How often the black hole formation occurs. And since this failed supernova does not emit any optical signal, and this such can be detected directly via neutrinos or gravitational wave. Also, another important term is the spectrum of each CCSN. Since we did not success the simulation in 3D dimensional, and this spectrum does not well understood. Anyway, some models are proposed, and this is a expected flux. This along in a few MeV to 50 MeV, and different color shows the different temperature of the supernovae. And there are also another neutrino source such as a reactor and solar neutrinos, like these regions, and another source is atmospheric anti-electron neutrinos and this energy. So energy window open for the super K is like this region from 10 MeV to 50 MeVs. And this, also is a good probe to average the behavior of supernovae in universe with such as temperatures. In the water channel detector, this is a detection cross-section or plot. And SRN signal has consists of all flavors of the neutrinos, electron, muon, tau neutrinos, and its anti-neutrinos. From this cross-section plot, this dominant channel of the SRN is the inverse beta decay, drawn in the black line. Anti-electron neutrinos and proton go to the positron and neutron. And also other channel is order is electron neutrino and neutron go to electron and protons. However, this channel has a large background, and water channel detector cannot distinguish charge sign, positron and electron. So the difference in the channel detector is only this proton or neutrons. In the super Kamiokande, is introduce the neutron tagging method in order to reduce backgrounds such as solar electron neutrinos and solar electron neutrinos. This method available from the 2008 since we introduced the new DAQ system. This enable is to take the after trigger so-called long-term data taking, long-term data equation, so we can check this signal. Its principle is we see the neutron captured by the hydrogen in water. This is a schematic view. Neutrinos interact and then emit the neutron. This are summarized in the water and then captured by the proton of the hydrogen. The 2.2 MeV gamma ray is generated. Since this 2.2 MeV very weak for super K, there are only 10 photons detected on the PMTs. So the tagging efficiency is limited to the 20%. This is not enough for this physics. This is a highlight of the today's SK result. Since we have not observed any signal of the SRN, so we set only the upper limit of this flux of the anti-electron neutrinos. This is in robust to the model independent result. This red color shows the SK's latest result. This X is the neutrino energy and Y is the flux upper limit. And other different color shows the old SK analysis. And yeah, however, this black color shows the Kamran result. This is not the water chemical detector, but this is a scintillation detector. So this Kamran experiment can reach some lower energy region. And this is SK's type upper limit. And this region is covered by the blue. Blue is the predicted SRN flux. So we are now close to the model predictions. In order to enhance the GSSRN signal efficiency, we are now loading the gadolinium, which has the largest neutron capture cross-section in the nuclear. And this is the schematic. Neutron capture is the gadolinium, and then this gadolinium emits the several gamma rays. Total energy is 8 MeV, slightly high, so we can enhance its neutron tagging efficiency to the 90%. This is the final design of the SK gadolinium loading. And this project started from the 2018. In this term, we refurbished the Super K, and we fixed the water leak. And this year, we loaded the gadolinium in the Super K. Amount of the gadolinium is 0.01%. This is not enough to the final design, but the tagging efficiency is now about 50%. This is a picture in the refurbished work of Super K 2018. We drained the pure water from the Super K and opened its tank. And yeah, we fixed the water leak. This is very huge, and this is a PMT used in the Super K. And this summer, we dissolved the gadolinium in the Super K. This is a water system, and light picture shows the gadolinium sulfate to be dissolved. We installed the gadolinium from the bottom region, and it took 1 month. We finished the 0.01% in mid-August. So now we saw the some gadolinium signals. Light plot shows the cosmic muon separation background of the neutrons, and top is the energy spectrum and different color. Red is a play before gadolinium loading, blue is after gadolinium loading. We see some excess around the 6 MeV region, and bottom is a capture time plot. Number of the neutron captured by the something is increased efficiently. So this gadolinium works well, and we are now aiming to first detection of SRN in coming several years. Also, we have another project, Hyper Kamiokande. This is a future project in Japan, but we have some international collaboration, and this third generation huge water chemical detector. left small is Kamiokande and second generation Super K. Third is Hyper K. Its dimension is diameter is about 70 meter by 70 meter. And this neutrino target is also about 8 times larger than the Super K 200 kiloton scales. This is a PMT mockup, and right bottom picture shows the Hyper K site. This is the center of the cavity. We started its construction in this year, April, and we plan to start operation in 7 year 2027. And this plot shows the prospect of the post SRN analysis of the Hyper-K. And the plot shows the expected spectrum. Red is the background, and this green black shows the signal and background. Expect for the separation background. This Hyper-K error is a spectral measurement. We aim the spectral measurement. We expect 10 to 30 events in 10 years operation. And this enables us to model test and effective temperature measurement. This is the difference of the supernova temperature, red and black. And also, this dot line and solid line shows different black hole formation fractions. The open energy window is about 50 MeV to 30 MeV regions. And yeah, in the laboratory, I developing the timing estimation system for Hyper-K, and this is the schematics, and timing information of the photon detection is crucial for the construction. So this system synchronizes 2000 volts with sub-nanosecond precision. This is a prototype code. Let me summarize. SN1987A, Kamiokande-2 observed several neutrinos, and water chamber detector is a good type for supernovae neutrinos. And there are supernova-related neutrinos emitted by the burst and diffuse in space. Large water channel detector will be aimed at these detections. Advantage is a large statistics and lower energy threshold. Now Super K with Lagrangian is operating and aim to fast detection in coming 5 to 7 years, and Hyper K will start in 2027, and it is a era of the spectral measurement. That's all. Thank you very much.
Thank you very much. Very clear talk. Questions, comments?
Sorry, can you hear me? I
Yes,
wanted
yes.
to ask one question. Yeah, so you said SK cannot distinguish between E plus and E minus from the Cherenkov. In one of your slides, you showed that, right? So how the E minus is produced? It's from the okay, neutrino with neutron. Okay.
Yeah.
Okay. I see. Okay. But you can distinguish between them from the neutron tagging, right?
Yes, so we can reduce background.
Okay.
Yeah.
But this cross section or the probability for both these processes should be similar, right? Or you have less for one, or
These are about 50 MeV region. This cross-section is almost same, but these regions are dominated by the atmospheric neutrino background, so we are interested about this lower region.
Okay. All right. Okay, thanks.
Yeah, oxygen is a nucleus, so you need some nuclear barrier.
Yeah, right.
It's not free neutron, unfortunately.
Yes.
Other questions or comments?
Hi.
Yes.
I have a very nice question. So in the summary page, you show that that currently there are two efforts from the Super K and Hyper K, and of course, as you mentioned, as you described, the characteristics of the two measurements are different, and also the sensitivities are different. but it looks like they are starting in similar time scale. So I was wondering if measurements are starting in the similar time. Which one is which one is better? I mean, which one is the more sensitive to the first detection?
Yeah. Detector principle is almost same as expect for the gadolinium. And yeah, it's defined by this measure flux is determined by its statistics, and yeah, we enhance the signal efficiency with the gadolinium and coming we aim fast detection in several years. Yeah. Mm. Sorry, I did not answer clearly.
Yeah, but so if it happens in several years, and then if the hyper-K starts from 2027, which is 7 years from now, I was wondering if, so since the human resources are limited, I'm wondering if you have to spend the human power through effort. I think most of the people working on this are working on both projects. Right?
Yeah, Japan group efforts are both project, I think. Yeah.
Anyway,
Yeah.
so that's naive. I need to answer this.
I see.
Hey, just a comment from Shovan here. Yeah, I think, but even for hyper K, it will take at least couple of years to get the sensitivity of super K. So maybe it's not. I mean, I don't remember the exact time hyper K required to reach. Because I mean, what we're getting in super K in 5 to 7 years with gadolinium, I think you need like at least more than a year or 2 years to get such sensitivity in hyper K, right?
Yeah. For now, we plan.
Okay.
We don't have any plan to introduce Cadre Hyper-K. Yeah. It needs about 10 years operation for spectral measurement.
Yes, yes. So that's what exactly. I was saying yes. That like I mean, hyper K also to do the spectrum measurements. I mean, even for detection, you need at least couple of years, right?
Yes, yes.
Yeah. So in that sense, super K and hyper K may not compete. Like you might have the detection before hyper K start doing detection in super K.
Yeah.
Yeah.
Of
Yeah.
course. Thank you
That's
very
my
much.
comment. Yeah. Yeah. Yeah.
Yeah, thank you for nice comment. Okay, I think so almost time is up. So let's thank all the speakers in this session again. Thank you very much. And we have a break, about 15 minutes, and start the next session at 11:30 Indian time and 3 p.m. in Japanese time with chair of Professor Saito. So thank you very much.
Can you see my screen?
Yes, yes.
Yes, we can see.
Okay. Just wanted to check. Okay, it appears to be working. Okay, thank you.
Okay, so it's about the time to start the session 6, electronic structure of physics of materials. And there will be 3 speakers. And the first speaker is Professor Sabhardeep Ghosh. His talk is entitled Quantum and Pseudo Capacitances of Mexican Supercapacitors. So could you start?
Yeah, thank you, Professor Saito. It's nice to see you virtually
Nice to
though.
see you again.
Yeah, so let me share my screen first.
Yes, please.
Yeah. Yeah, is it visible?
Yes.
Yes, we can see it.
Oh, okay, yeah, just a minute. Let me adjust it because, yeah, okay. Yeah. Somehow it got stuck in between, so I will just trying to go back to the first one. Yes. Okay, so good morning, everybody in India, and good afternoon in Japan. I'm going to talk about quantum and pseudo capacitances of magazine-based supercapacitors. This work is done with Mandira Das, who is my PhD student. The work is far from being over, but we have got some interesting results, and the magazines are the new blocks in the family of 2D materials. It's just about 10 years old, and there is a lot to be explored yet. So I'm going to show you some preliminary results, and I hope that it would generate some interest, and we can get some directions from the discussions. So first, let me start with a very brief preliminary on what is a supercapacitor. It's basically, we all know what is a battery and what is a supercapacitor. Both are the materials for storing of charges and basically delivering the energies. So here on the left-hand side, you can see the plot of power density versus the energy density. So power density is basically speed at which the energy can be delivered to or absorbed from the load, and energy density is basically the energy per unit mass. So we can see that the energy density of the batteries are high, but the power density of the capacitors are much larger, and the electrochemical capacitors or the supercapacitors, they basically lie in between with a pretty good power density and pretty decent energy density as well. So here is a little comparison between supercapacitors and battery. You can see that supercapacitors are order of magnitude faster in terms of charge discharge time. The specific energy count, of course, is lower than the battery, as I had just told, the specific energy or energy density. The cycle life is much higher, that it can sustain over 500,000 cycles in comparison to battery. Typically, the one you use in the mobile phones, that can sustain about 1,000 times. The specific power certainly is, very large in case of supercapacitors with comparison to battery. And this Coulombic efficiency, that is the total charge that can be extracted or total charge put over a cycle, is very high for the supercapacitors as compared to battery. So that is why it's a bridge between capacitor and battery, and is gaining quite a bit of traction. So on the right hand side, this small figure is actually giving us some idea about the supercapacitor arrangement. So essentially here we have a 3 electrode arrangement. You have materials which are coated with, those are anodes and cathodes, basically coated with these magazines or something else. And there is a separator in between in order to avoid the short circuit. And then there is basically, these are the working electrodes, these anode and cathodes. And then there are 2 other electrodes called reference and counter electrodes. So the reference electrode is a standard material electrode whose potential is very well known. So the potential that we kind of set for the measurement sake, the potential is set with respect to this reference electrode. This counter electrode or the auxiliary electrode is basically in conjunction with this working electrode, it provides a circuit over which the current is either applied or measured in a voltammetric analysis. Potential of the this auxiliary electrode is not really measured and is just adjusted to balance the reaction occurring at this working electrode. This entire setup is immersed in a electrochemical solution, in an aqueous solution, and then there are electrolytes. So these electrolytes actually move into this system, and then they sort of move around and move towards either of the working electrodes, and this separator is essentially takes care of so that the short circuit does not happen. So in a nutshell, this is the arrangement. Now what happens, how the charging mechanism works, or the components and contributions that gives rise to supercapacitor, as the name suggests, it must have a very high capacitance as compared to our standard capacitors. So here is a cartoon diagram that you can see that we have the two electrodes, positive and negative ones, and then we have a separator. Now when we have put it into an electrolyte. So when we connect it to a battery, what happens is that there are two layers of charges. So on one side, you can see in the negative electrode, what we had expected is there will be a piling of the negative charges, and on the positive electrode, there will be piling of the positive charges. But now we have the electrolyte solution. Now, due to application of voltage, the molecules of the electrolyte, they get the charge separated. So basically, the positive charge ones, they move towards the negative electrode, and the negative charged ones, they move towards the positive electrode. Now, what happens that they do not really reach the electrode, but in between, there is a very thin layer of nanometer dimension made usually by the water. So this is like happens like works like a molecular capacitor. So instead of a dielectric, there is this water actually plays the role of the dielectric in between. So there is a very small distance between these two layers on the both sides. So this gives the so-called effect of the electrical double layer, and the capacitance can be calculated, in the usual form, which is on the left top corner. The CEDL is epsilon A by D, where the A is the area, surface area of these electrodes, and D is the distance between the two layers of charges. So what happens now, you have a positive and a negative electrode, and they are actually connected in series. So that gives rise to a very high capacitance because your D is of the nanometer order. It's very low. And then if it is a 2D material, then the surface area would be very high. Now, this is not only the contribution to the capacitance. Now, some of these electrolyte molecules, they can actually permeate through this thin layer of water, this thin layer of molecule, dielectric, so to say, and they can actually make some charge transfer with the electrode material. So there is this redox reaction due to this charge transfer, and what the contribution to that can be easily calculated by calculating the charge transfer with respect to the applied voltage. So this contribution is known as pseudo capacitance. So the pseudo capacitor and the EDL, they are in parallel. So both of them contribute heavily to the total capacitance. And on top of that, there is another contribution which I have marked here as CQ, which is parallel to the whole arrangement, to which I'm coming. That is called the quantum capacitance, which is an inherent property of the material. So this is how the supercapacitor, the very large capacitance is obtained when you subject these electrode materials into electrolyte solution. So what are the factors affecting the capacitance value on the basis of charging mechanism? As I said already, that you can have the electrical double layer capacitance or the pseudo capacitor, and you can have both, which is the hybrid capacitor. Now it depends crucially upon the electrode material and the type of the electrolyte. Now, as I said that particularly for the EDL, the surface area is if it is very large, then you get a very large capacitance because your D is already low. So naturally, the materials with large surface to volume ratio are basically sought for. So 2D materials are definitely the choice of people. So as electrode materials, the first thing that comes to our mind is this 2D nanomaterials, where this D is also, in the nanometer scale. So one of them is this transition metal oxides, transition metal dichalcogenides, on which a lot of work has been done. They are well known for various other properties. Or we have graphene, the blue-eyed guy of this 2D family. And then we have this new block in the series is magazines. So why magazines? What are they? I'm going to tell you very briefly. So first, let us see that what are the values that we get out of these various 2D materials. So reduced graphene oxide, that gives you about 135 farad per gram and 99 farad per gram in aqueous electrolyte and organic electrolyte. The transition metal oxide family, manganese oxide nanosheets, they get pretty good specific capacitance. And then you have layered, double hydrides of iron and cobalt. They also give kind of pretty good specific capacitance. And then there is, of course, transition metal dichalcogenides. However, then why magazine and what do they actually give us? Now, the advantage of magazine is basically a new class of materials. So it is essentially derived from what is known as a max phase. Max phase is a three-dimensional stuff in a hexagonal arrangement where you have basically M, which is a transition metal. You have X, which is typically carbon, nitrogen, or germanium kind of things. And then as A, you have the aluminum. So you can see over here, these three figures are basically various, stacked layers of these max phases, where you can have these red ones are the transition metal atoms. The small white ones are this X, that is carbon, nitrogen, etc. And then they are basically interspersed by these aluminum layers. So from this max phase, the derivation of magazine is basically nothing but this 3D is reduced to a 2D system by simply chopping off these aluminum layers. Then you get basically 2D sheets of M and X. So in 2011, the first one was produced by Yuri Gogotsu's group. So this is the paper in advanced material. So they exfoliated this titanium 3 aluminum carbide and produced titanium 3C2. So here is the snapshot of what actually happened. So essentially they had put it into a hydrogen fluoride aqueous solution, and which basically exfoliated. So they got rid of the weaker bonds, and aluminum was completely chucked out of the system, and you got 2D sheets of this titanium carbide. So then after this HF termination, what they do is they put it in an aqueous solution. So they did the sonication, and then they got this nice 2D sheets. So here is the reactions that had happened. So what you can see is at the very end, what you are getting is essentially, there is not just Mn plus 1 Xn, where here the M is Ti and X is carbon, but also there is other functional groups being attached to them. This is called the surface passivation or the functionalization. You cannot really, while you prepare it this way, you cannot really get rid of this. So either fluorine or the hydroxyl group gets attached to it. Okay, and then hydrogen is also produced. So this was the very first paper, if I remember correctly, of producing maxins. And then not only that, they further measured the capacitance. And you can see that these were the reported results, again by Gogotsu's group, that it was 350 farad per centimeter cube, whereas for graphene, it was 60 to 100 only. So you are getting a very large capacitance in this maxine system. And then they further went on, the other group from China, they had actually found out that if we dope this titanium carbide with nitrogen, you can get, 192 farad per gram or 82 farad per gram kind of things, So basically, if you do not dope with nitrogen, it is 34 and 52 respectively. So you get nearly 5 times of increase by doping nitrogen. So because of this very early research, the maxine has drawn attention in the usage as a supercapacitor, and this is why we got interested into it. So, well, one point that I had mentioned while showing you this cartoon diagram of this charging mechanism is there is one component which is CQ, which basically comes from the electrode material. So impact of the electrodes is that often, the electrodes is being neglected, that in a typical metal, dielectric metal capacitor, what one thinks is that the electric field inside the electrode is completely screened. So whatever capacitance effect you see is really coming from the dielectric itself. So in case of supercapacitors also, the same thing can be thought, that it must be coming from the electrolytes alone, that is the EDLC, and then certainly whatever is there, the charge transfer between the electrolyte and the electrode material is the only contributor. There is no inherent contribution from the electrodes, but actually there is an impact from the electrodes. The electric field inside the electrodes is never completely screened. That leads to an additional capacitance which is known as the quantum capacitance, and basically this goes in parallel with what is known as the geometric, what we just discussed is the geometric capacitance. So as a result, due to this quantum capacitance, the overall capacitance of the system actually gets decreased. In fact, this idea of quantum capacitance or the impact of quantum capacitance is large in case of the 2D materials, which was nicely presented in this paper by Louis et al., where they had actually shown that in this setup, if you have this one capacitor plate and another capacitor plate, and in between, if you put a metallic grounded plate, there is from the point of view of this one, there should not be any sort of charges being piled up on this side. Okay, but actually when it is a 2D electron gas kind of thing, that does not happen. The electric field is not totally screened and there is charge piling up on this system. So from the point of view of the plate one, this is actually the capacitor arrangement where the CQ is this quantum capacitance. So quantum capacitance is something that we cannot really get rid of. So the quantum capacitance is completely a nanoscale effect, and you can calculate it from the variation of charge density with the electrode potential. And as I said, for low density of states materials like 2D ones, it is very important. So this is the Louis paper that I was actually going to was telling you about, and this is one formula they had worked out. So this is how we calculate the quantum capacitance of a material. You can see that this quantity inside the integrand is the densities of states, and then there is this Fermi function. Finally, this is the form of the Fermi function. So at any arbitrary temperature, you can calculate the differential quantum capacitance, but more interesting is the integrated quantum capacitance, because as I said that when you charge the system, you basically charge to a particular voltage. So therefore, the integrated quantum capacitance is the quantity of interest. Now, how do we compute the pseudo capacitance? Here we have used one particular formalism, and that formalism was based upon the fact that the electronic structure of a material does not change if electrons move in or out from the system. As I said, that the pseudo capacitance arises from simple charge transfer between the electrode material and the electrolyte molecules. Therefore, it is about simply giving or taking the electrons in and out. Therefore, there should not be a significant change in the electronic structure. The only change should be through a rigid shift in the position of Fermi level. This is known as the rigid band approximation. Subjected to that, what we did is we considered a charged electrode, because that is it all about, that when you connect it to the battery, it is charged already. So in the charged state, we consider an electrolyte solution having positive hydrogen ions, and then we study the impact of hydrogen ion on electrode surface by looking at the charge transfer and the changes in the work function, as this hydrogen ion systematically covers the entire surface. And then we actually calculate this delta V from the changes in the work function. Okay. Now, what is the focus of this work is basically computation of quantum and pseudo capacitance of pristine and functionalized magazines. There are several of them. Some of them are being processed. They are being experimentally manufactured, but some of them are yet to be manufactured. So we are trying to give some insight into the experimentalists. And you can see the transition metal here is from both 3D and 4D series. So we wanted to also do a comparative analysis of magazines from 3D and 4D series. And then we try to provide ways to enhance functionality of these compounds in the context of supercapacitive applications. So what we did was using density functional theory, the VASP code, we had done all the calculations. So first of all, let me show you the model that we have used. This is the structure of this M2X and M3X2, that is one extra layer. So that so this is basically the top side view and the top view. We can clearly see the M and the X atoms. Now, when the functional group is attached, as I said, the importance of the functional group, you cannot really, in an experiment, you cannot really throw them away. So it is important that where the functional groups actually get attached. So here are the various models of the functional groups. So on the left-hand side, you can see the model 1, where the two functional groups are sitting exactly on these two M atoms. In model 2, the functional groups is actually sitting in a position, a vacancy, where if you look below, there is no X atoms over there. You are directly seeing the M atom in the lower layer. In the model 3, it is a mixture of the two, that one of the functional group is sitting on top of this, basically sitting on in a position where it can clearly see the bottom X atom, and in another case, it is sitting in a position where it actually sees the M atom in the lower layer. And model 4 is where both the functional groups are occupying sites such that right below they are just sitting on top of these X atoms. And these are the models also for the M3X2. So subjected to that, we first calculated the stabilities of the functionalized maximums, and these are the results. Largely, they preferred the model 2 for all the different magazines with all the different functional groups. So what we concluded is that functional groups prefer to attach to the hollow sites in a homogeneous way, and you have a greater stability for the OH functionalization. However, when it comes to the capacitances, we first calculated the quantum capacitances. So these are the results for the pristine magazine. And I would like you to sort of concentrate on this part of the voltage axis, because you see, you cannot really, I mean, it's completely useless that if you run your calculations for an arbitrary voltage, because the voltage of which you can apply is limited by the fact that the electrolyte should not, dissociate. So the stability of the electrolyte is very important, and typically it is between -1 volt to +1 volt. So we had chosen the case where from 0.5 volt to 0.8 volt, what is the situation? And you can see that for both positive and the negative voltages, it is the green curve, that is the titanium carbide, is giving you the largest quantum capacitance. And then it is basically being followed by the vanadium carbide. So both from the 3D elements, the 4D ones are giving much less quantum capacitance. Now, when we go to the oxygen functionalized maxim, I'm going to show only result for oxygen functionalized maxim. You see more or less the similar thing, that here the V2 is very large as compared to the others. And then you have, at least on the negative side, well, there is this molybdenum, and on the positive side, there is this niobium. But certainly for V2, functionalized or not, the quantum capacitance is very large. So this can be understood basically from the electronic structure close to the Fermi level. So you can see that for the titanium carbide, for example, for the pristine one, the first one, there is very large density of states at the Fermi level, whereas with the oxygen functionalized, there is hardly any density of states. In fact, it is a insulator, and it impacts actually the quantum capacitance. So you can see that the titanium carbide is very low, having a very low quantum capacitance. If you go to a 4D system, the 4D bands are much more spread out. So therefore, the density of states close to the Fermi level is low as compared to one with a 3D material. And so you get a lower quantum capacitance in this case. Now, we also calculated the pseudo capacitance result. So first, let me show you the pseudo capacitance and the quantum capacitance side by side for the pristine compound. So you can see that the order of magnitude of both quantum capacitance and the pseudo capacitances are same for both the cases. And certainly, once again, here also the 3D materials have a larger pseudo capacitance as well. But when you go to the functionalized ones, then you can see basically the pseudo capacitance is order of magnitude smaller, at least for vanadium carbide. So vanadium carbide, for example, in the negative electrode, it's 1800, whereas in the redox or the pseudo capacitance is just 166. In fact, if you take the EDLC out of the equation and simply make a parallel connection between these pseudo capacitance and the quantum capacitance, the result comes out to be somewhat around 157 farad per gram, which is actually pretty close to a recent experiment. So for example, let me show you. So this is a very recent paper in 2D materials in the March month of 2020. So they actually measured the capacitance, total capacitance of the vanadium carbide magazine, and their maximum capacitance came out to be 164 farad per gram on the whereas we are getting 157. So it's pretty close, although we did not consider the EDLC into it. So this is interesting. This is to be sort of examined. So what are the observations that we get is that both capacitances are best for pristine maximes and have same order of magnitude. However, pristine maximes are hard to realize. So with oxygen functionalization, both capacitances decreased in general. Only V2C is the exception. Its quantum capacitance does not decrease significantly. Performances are certainly better for M being a 3D element. And basically, although there are materials which are isoelectronic across the 3D and 4D series, but that doesn't really tell us anything. Still, the 3D material-based maximes perform significantly better. And in general, both capacitances have magnitudes in the same order, so that overall capacitance is less in comparison to either pseudo capacitance or quantum capacitance, only with the exceptions of V2C that I just mentioned. So the prospects is that we need to investigate further, for example, this V2C, and then a very recent paper also in 2017, you can see that nitrogen doped magazine electrodes for high performance capacitor. So with nitrogen doping, you can get nearly 6 times increase in the capacitances. So therefore, in lieu of a summary, what I would like to say is that we have to still work on enhancing the quantum capacitance so that its effect is diminished and we get largely the impact of pseudo capacitance or the EDLC. So for that, we need to do nitrogen doping, because nitrogen doping will increase the densities of states close to the Fermi level, leading to an increase in quantum capacitance. Or we can apply the strain, which has actually worked for a molecular capacitor. So we can try that also. We really need to understand the comparative impacts of the
Hello? We can't hear Professor Ghosh now. Let us wait for a while. So, Professor Ghosh, can you hear me? So it seems that the connection from Professor Ghosh has been terminated. Let's see. Let us wait for a while if he can come back. Yes, it seems. Professor Ghosh?
Yeah.
We couldn't hear the last part of your last slide. Could you share
Yeah,
your
yeah,
last?
sure. Yeah, certainly.
Yes.
Okay, all right. Let me get back to my slides. Can you hear me? Hello?
Yes, I can hear you.
Yeah. Okay. All right. So, was it the summary slide or before that?
In this slide, we could hear until application of strain or so.
Oh, okay. All right. So what I was telling, yeah. So application of strain is one way to enhance the quantum capacitance. But what we need more is basically understand the comparative impacts of the various functionalized groups. So for example, here I showed the oxygen functionalized groups only, but there can be other ones like the fluorine or the hydroxyl group. So we have to, and in the experiment, it's very difficult often to figure out that which groups are there. So the comparative impacts and the understanding of the behavior is very important. And finally, we'd like to calculate the double layer capacitance effect, because that will add to the overall capacitance. And for that, we really need to do the molecular dynamics. So those are the things that are yet to be done. Of course, the first result that we got with the oxygen functionalized group for the vanadium carbide is very encouraging, because the recent result and our calculations are very close. So therefore, it sort of gives us, more sort of enthusiasm to dig further. Okay. Thank you.
Thank you very much.
Yeah.
Okay, so now paper is open for discussion, comments, questions.
I have a question, if I could ask.
Yes.
Professor Ghosh, thanks for the nice talk. Just wondering that how would you correlate the density of states at the Fermi level with the capacitance, either the quantum capacitance or the pseudo capacitance that you have been calculating?
Oh, okay. So for the quantum capacitance, if I go back to this thing, the density, the formula, there is the density of states onto it already. So here is the one. So you can see that it's the density of states convoluted with the Fermi function. So it's very close to the Fermi level, things are happening. So that way it can be correlated. And for the pseudo capacitance also, it's about the charge transfer. So you have this material, the electrode, and the electrolytes, say for example, the hydrogen ion. So it's basically systematically giving you electrons one after another. I mean, you try to cover the entire surface with hydrogen ions continuously, and you are basically gaining electrons. So that essentially is shifting your Fermi level. So therefore, the densities of states at the Fermi level or close to the Fermi level would have the impact.
Okay. So do you see a kind of a pseudo gap at the Fermi level? I mean, there's not much of density of states that I have seen in the figure in the plot that you have presented.
Okay. So for example,
this
yeah,
one.
so this is, yeah. So for example, with oxygen functionalization, it is horrible. I mean, it becomes a semiconductor. Okay, but that's just for the titanium carbide. Now, these results I haven't discussed, but you can see with functionalization, certainly this actually decreases, and this is expected. So that is where the challenge is, that quantum capacitance, for example, we want it large because it is connected in parallel to the rest of the capacitances. So if we can make it very large, the impact of that would be very small to the overall capacitance. So whereas with functionalization, it's the opposite effect. That is why by doping with nitrogen, say, okay, which has more electrons than carbons, if we could produce enough densities of states close to the Fermi level, then we will have a larger quantum capacitances. Now, regarding the pseudo capacitances, it's not yet very clear to us yet, because the pseudo capacitance, it depends on how the work function changes. So the change in work function with doping we are not yet sure of. But certainly the density of states close to that, the functionalization reduces, as you can see in the results, that from the pristine with the functionalization, both the pseudo capacitance and the quantum capacitance decrease. So therefore, there has to be ways to increase, the situation, so that we get handsome density of states close to the Fermi level.
Okay, thank you.
So we may accept one short question, one more short question, if there are any.
So can I ask?
Yeah. Yes, please.
Yeah, Professor Ghosh, you have shown that response of quantum capacitance on voltage, and for some compound it was symmetric, but some compound it was not symmetric with voltage.
Well, I don't know really. I mean, whether that symmetric or non-symmetric has any meaning, because it seems a bit arbitrary at this moment.
Okay.
So honestly, I don't know.
Okay, thank you.
Okay, I'm afraid that we are running out of time. So let's thank Professor Ghosh.
Yeah, thank you.
Okay, so the last speaker of this session is Professor Sadhash Thota, and the talk is entitled Reentrant Spin Glass State and Field-Induced Transistors in Spinels. Yes, we can see a slide. Good.
Thank you. Today's talk is on reentered spin glass state and field-induced transitions in some of the spinels. This work is done by my PhD students, and I'm presenting this work. So this is the outline of my presentation. First, I'll give brief introduction and motivation why we are doing this particular work, followed by the experimental details. In the results and discussion, I divide especially two classes. The first one, we deal with the reentered spin glass system in the geometrically frustrated case. And the second one is concentrated on the field-induced transitions and how the structural phase transitions drive the system to show the disordered state. In particularly, I'll stress the points tetragonal distortion and the John-Taylor activity, followed by summary of the results. Well, you guys know that spinels are the gemstones, basically. These are very hard materials after diamond, and then the different beautiful colors we can see due to the defects present inside the system. Magnetic spinels, particularly, they have the isostructural MgAl2O4 type of structure, and they are classified into two systems, particularly normal and inverse, having the general formula AB2O4. So here in the normal spinel, all the B cations, whether it could be tetravalent or divalent, they occupy the octahedral sites, whereas the complete A atoms occupy the tetrahedral sites. In case of inverse spinels, all the A atoms will go and occupy the tetrahedral sites, but half of the B atoms can go and sit into the tetrahedral sites. It's also possible that mixed spinels can also exist in nature. Okay, you can see this particular figure where the B atoms are occupying the octahedral sites and the tetrahedral sites by A atoms. The typical unit cell is 8 angstrom units, and there is a plenty of scope of the doping and substitution in this particular big unit cell, having 32 oxygen atoms and 8 A atoms and 16 B atoms. It's very interesting that spinel sometimes they share the tetrahedral corners, and then they exhibit the pyrochlore type of structures. As we know nowadays, these 2D Kagome and the 3D pyrochlore structures, they offer unconventional magnetic states, particularly the spin liquid states and geometrical frustration and all other stuff. So we will discuss such kind of results also in this particular talk. Spinels are having a lot of applications, especially in the renewable energy sector as well as the magnetoelectronics, specifically in high density magnetic storage media, because they show the exchange bias effects. So these are motivated us to work in this particular systems. There are basically two types of exchange interactions in this particular system. Spinels. The dominant one is the super exchange interaction. It depends on different paths, basically, whether it could be 120 degrees or the 90 degrees. Depending upon this particular angle, their electrical properties also changes widely. So why the reentrant spin glass behavior? What is reentrant spin glass behavior? In any magnetic system, if we increase the temperature, what happens? The disorderness will increase. After certain temperature, all the spins are randomized, and complete disorderness you can see in this particular system. So here the arrow marks represents the spin disorderness in the system. The moment we go to the lower temperatures, the orderness increases, and then it can show either whatever the magnetic ordering it will be, whether it could be ferro, ferri, or anti-ferro. And we expect that we further go to the lower temperatures, then phonons will be freeze down, and then we expect the long range ordering can be even much more strengthened. But this can't happen most of the times in case of geometrically frustrated systems. Sometimes what happens, the exchange interactions, particularly the competing exchange interaction between the spins, that can drive the system to exhibit the disorderness again. Like we see, it is not exactly equivalent to the state of the disorderness at high temperature, but at low temperatures, these spins basically follow some kind of scaling laws, and then the state we call popularly is known as spin glass state. So glassy, that means disorderness is there, but these spins still interact with each other below the spin freezing temperature. So this is very stunning thing. And then this re-entered disorder state basically contains a lot of rich physics. Sometimes they show the geometrical frustration and very high exchange bias and other kind of magnetic ordering in the system. Well, in order to probe such kind of re-entered system, we have chosen one particular element in the periodic table, that is cobalt, which is a strongly correlated system and having a very good local spin. What we are doing in this pristine case, it is the antiferromagnetic system. However, when we remove one particular cobalt with the non-magnetic element, like either tin, titanium, ruthenium, or germanium, its structure changes, and depending upon the diffusion of these particular elements inside the parent matrix, they can show the different types of magnetic ordering inside the system. For example, CO304 is popularly known as a normal spinel, showing very good antiferromagnetic properties with nil temperature around on 30 Kelvin. And the other systems, when we incorporate this non-magnetic element, they show completely different magnetic properties, particularly the re-entered spin glass behavior, magnetic compensation, ferrimagnetic behavior, and sometimes they show still antiferromagnetic behavior with different exchange interactions. Well, this particular paper motivated us to reinvestigate these systems, appeared in 1977 by French authors. What they figured out that these dilution can bring very high coercivities in the system. We can see that coercive fields as high as 40 kiloarsted, and then magnetic moment increases, but the magnetic moment drops completely to zero when we go to further lower temperatures. So this particular paper, and then 1987, one more paper that is you can see this. We can see the Gabay-Tholos mixed phases when we measure the AC susceptibility versus temperature at different levels of the DC field superimposed. So what these particular peaks are representing, and how to interpret the data. So on that basis, we investigated the system. First of all, the tin-based system, where we have the complete non-magnetic element SN4+, plays a key role, because you see here magnetization versus temperature, it drops quickly below 40 Kelvin. Up to this particular point, it shows wonderful ferrimagnetic properties due to the imbalance in the magnetic moments. The net magnetic moment is 1.04 mu b due to the different magnetic moments of the A site and B site cations. Well, okay, once we got this particular, we will investigate the low temperature magnetic properties by the AC magnetization also. Its sister system, however, shows completely different magnetic properties. For example, I replace, instead of tin, I replace with the titanium, which is also having 4+ state, known magnetic moment, and the size of this particular ions also approximately same because of the same family. But you see the magnetization versus temperature, it's distinctly different. It shows the compensation behavior where the two sublattice magnetizations balances with each other and the net magnetization is 0. So this is this kind of different magnetic properties motivated us to investigate in two aspects. One is what is the exact ordering of this particular system? What are the temperatures? And the next is what is the low temperature magnetic structure of this particular system? Okay, so for that purpose, we want to know exact cationic distribution in this particular system, both whether it is non-magnetic elements are completely dominating the low temperature properties or not. For this, we have measured the inverse susceptibility versus DC susceptibility versus temperature, and when the paramagnetic data we fitted with the Niels expressions for ferrimagnets, and then we obtained the asymptotic Curie temperature, which gives the antiferromagnetic exchange coupling strength, and then the molecular field constants, and then the exchange interactions. But you see the effective magnetic moment, what we observed is 6.5 mu b per moment. If we choose CO2 plus at A sites 3.87 mu b for S equal to 3/2 ground state, and then we obtain the B site moment as 5.19 mu b. This is far higher than the S equal to 3/2 of the cobalt. So, okay, what we did, we try the combination something like this. Here we chosen titanium 4+ moment is 0, but here titanium 3+, we thought that okay, why not titanium 3+ also possible, and it having one spin having 1.73 mu b. And then we calculated the reverse calculation yields the CO3+ moments 4.89 mu b. So this is the astonishing result that this CO3+ having the high spin magnetic moment equivalent to 4.9, excellent agreement with the magnetic moment of the CO3+ in the high spin. So then we thought that okay, we will check the titanium 3+ presence in the sample that is driving the system to show the ferrimagnetic and then the compensating behavior. So from that we concluded that okay, the electronic structure of this system is not Ta4+, in fact Ta3+ and CO3+ in the octahedral site. Well, so direct proof we obtained from the X-ray photoelectron spectroscopy measurements, where first we figure out that whether CO3+ having mixed states or not. So you can see on the screen the intensity versus binding energy peaks, the cobalt 2p 3/2 and cobalt 2p half, and these particular doublet, I am showing the inset of this particular figure, where the distance between the energy difference between the peak, the D1 to D3 is 15 electron volt, representing the CO3+ presence. But in case of 2+, it is just lower than, just higher than the 15 electron volts, representing the CO2+. We compared with the standard CO304 spectrum. But in case of titanium, the direct measurements yields titanium 2p 3/2 and titanium 2p half. The difference is nearly 457.65 electron volt. If the perfect Ti3+ is present, it should be 457.7 electron volts. So our result is closely matching with the Ti3+ than the Ti4+. And cobalt 3+ presence also, we got the signature from delta E P2 minus P4. So the peak separation between the P4 peak on this particular figure B two figure the peak of CO2 P3 by 2 P2 that gives 15.43 electron volts, giving some signature of the mixed valency in the system. So with this we proceeded, and then we wish to investigate one more aspect, that since both are the sister systems, why this particular tin system is not exhibiting the compensation effect. So we systematically did the magnetization versus temperature measurements at very low fields. Then we figured out that yes, this system also shows the compensation effect, but the compensation is at very low temperatures, below the ordering of the long range ordering of this particular system. So what we did the differential susceptibility analysis, because it is closely related with the heat capacity. Generally, any transition, if we have order to disorder transition, it is the heat capacity data that can give the perfect location of the transition. Since this function, this chi dc versus t, closely related with the heat capacity, we took the differentiation of this particular plots as a function of temperature. So stunningly, we saw two distinct peaks, one corresponding to one magnetic ordering and second corresponding to the another type of magnetic ordering. So in the literature, such kind of systems are there. How they distinguish, because something like we have the transverse component and the longitudinal components. One particular component represents the long range ordering, and other component represents the frozen in state. So for example, in the present case, this transverse spin component represents the glassy type of disordered temperature, and then this particular spin wave, or you can see on the horizontal axis, that can give the longitudinal component is related to the long range ordering of this particular system. If we have such kind of glassy signatures, it is appropriate to do the AC susceptibility measurements. And this scenario is same for both the systems, tin as well as titanium. So what we did here is that we took the AC susceptibility versus temperature with very closely spaced temperature interval. You can see that 38 Kelvin to 41.5 Kelvin. When we measure this AC susceptibility measurements, using squid magnetometer on the samples that we synthesized by standard solid state reaction technique. Yes, 1200 means we sintered at 1200 degrees Celsius for 12 hours in air. 1350 means we sintered at 1350 degrees Celsius for 2 hours. Why? Because at high temperatures, I can remove the signatures of the tiny undigested non-magnetic oxides that present in the system. Anyway, both the samples show the more or less same signatures, where we can see the imaginary and the real component of the magnetization perfectly intensity drops, and then it shifts towards the higher temperature side when we apply the AC field of 4 oersteds. And we varied the frequency. With increasing the frequency, this wonderful dispersion in the frequency shift that gives the signatures of the spin glass state in the system. Well, what we did, we pick up this particular peak point, and then we applied the different scaling laws in the system, particularly the Vogel-Flocker law as well as the power law. So both these equations are the dynamic scaling laws that represents the spin glass type of nature in the system. If we obtain the logarithmic graph, if it is the straight line behavior. Well, it is showing wonderful straight line behavior when we plot the logarithmic variation of the time constant tau, and then the inverse difference in the temperature T minus T naught. Here T naught represents the same interaction like the freezing temperature. So using this particular fitting analysis, we obtained both the relaxation time constant as well as the freezing temperature, using both the data like the imaginary as well as the real components. So these are within the standard spin glass systems what we saw. But in case of the other compounds, let us see the other scaling law as well, power law. Power law, usually we should get this critical exponent value between 4 to 12 if it is a spin glass system, typical spin glass system. So in case of CO2 SNO4 system, of course, it is falling. The Z nu is between the 4 to 12, and it is giving the perfect spin glass type of nature. But on the contrary, the single crystals and polycrystalline CO2 TiO4, although they show wonderful frequency dispersion in the AC susceptibility data, but the mathematical analysis is not providing the convincing evidence of the glassy signatures. For example, the critical exponent that we got here is Z nu equal to 16, which is for beyond the limit of Z nu equal to 4 to 12. And another unphysical value that we obtained is that the relaxation time, tau naught, is 10 power minus 33 seconds. So from this, we figured out that, okay, although system shows the dispersion and the reentrant disordered nature, but we cannot directly relate it whether it could be a canonical spin glass or the cluster glass type of system. But yes, what we did, okay, is there any alternative way of judging this reentrant glassy nature? What we did is that we performed the same AC susceptibility measurements, but by superimposing the DC fields. We can understand this experimental technique something like, if you have a sea, upon the sea you have the ripple of this water. Ripple, you can imagine like the peak to peak amplitude of the AC magnetic field that we are applying, and then the depth of this particular sea you can imagine like as if we are applying the DC field, because the strength of the DC field that we are applying here is very high, 150 oersteds, as compared to the peak to peak with just 4 or 3 oersteds. Why this kind of measurements are needed? Because when we do this kind of measurements, we can able to separate the mixed phases in the system. Mixed phases in the sense that whether it could be spin glass and then antiferromagnetic or ferromagnetic, ferrimagnetic, whatever it may be. Yeah, we are successful in this particular kind of measurement. We can see that inside the inset, I'm zooming out the peak, that peak representing the two peaks. Okay, it is having a doublet, and this doublet represent one phase transition corresponding to the long range ordering and another phase transition corresponding to the disordered nature. So in the imaginary component, you can see the drastic drop in the magnetization when we increase the DC fields, and then it is also shifting towards the lower temperature side. So what we did, we pick up this particular peak point, and when we plotted this peak point as a function of h power 2 by 3, popularly known as D'Almeida-Thouless mathematical analysis, if the system is exactly spin glass nature, then it should show the straight line behavior that we can see on the screen. We can see the perfect glassy signature, perfect straight line behavior of the experimental data. And this is true in case of CO2 TiO4 also. Although we got the negative result in the frequency dependent studies, but we got the perfect results in case of the AC plus DC superimposed study, where we saw the perfect Gabay-Taulous mixed phase type of ordering in the system. Another astonishing feature is that it is the single crystal having very less defects. I should not say the completely defect free. The imaginary components show the negative sweep in the amplitude, but the polycrystalline, where all the grains are oriented in different directions, it gives no zero crossover in its imaginary component. However, it shows the perfect frequency dispersion towards the higher temperature side when we increase the frequency from 0.17 hertz to nearly 1 kilohertz. And though it shows the perfect validity of the power law as well as the Vogel-Flucker law. But the unphysical values that we got is really bothering, whether the system is really reentrant spin glass system or not. So in the literature, there is a competition between which power law we should use to complete legitimacy of this particular ordering. So among these two, it is best to validate on the basis of power law plus the AT line, D'Almeida-Thouless line criteria, instead of the Vogel-Flucker law. So in the present case, what we did that it is important to show the frequency dependence studies and rely on the frequency dependent dynamic susceptibility than the other laws. So you can see that here I extrapolated this particular horizontal axis to 0. The temperature at which the h power 2 by 3, this line is kissing the y-axis, that gives the glassy signatures of the system. And it's nice to see that whatever the temperature that we saw, 46.68 in case of CO2 TiO4, is matching with the spin glass freezing temperatures that we obtained from the frequency dependent studies. So another convincing proof that you can get from the heat capacity versus temperature, if you have a long range system, then you can see a very good sharp peak in the heat capacity versus temperature. But in case of these diluted systems, we didn't see any a very sharp transition across the long range ordering, but we can see a shoulder, and that depends on the external magnetic field also. We went up to 5 Tesla, and we saw the complete broadening in this particular long range ordering peak. So this gives the convincing evidence that, yeah, we have both the mixed phases. One is glassy and then the ferrimagnetic transition. But when we apply the high fields, you can see that 30.12 Kelvin, the magnetic ordering, due to the compensation, one sublattice is magnetization shoots out. That gives the hump here at 30.12 Kelvin. It is the same temperature, excellent agreement with the compensation point in our system. So using the mathematical equations, we can also separate out the lattice as well as the magnetic contributions, and you can see that magnetic contribution continuously drops when we are increasing the temperature because of the phonons, and the phonon part will take care at the high temperatures. At the low temperatures, yes, we have the magnetic contribution is higher, and the transition temperature is perfectly agreeing with the magnetization measurements also. So two different techniques, but yielding the same result. It is same in the case of CO2 SNO4 also. The glassy ordering is there. If we compare with the perfect AFM system, you can see on this particular screen, the heat capacity versus temperature data. It is way back reported in 1982 by Russian group. We can see this 29 Kelvin, it's 29 Kelvin, this particular data is in excellent agreement. The sharp peak, because the system is not having any dilutants. It is having perfect CO3O4 single crystal. The Néel temperature is 29 Kelvin. So in 2008, we did the same analysis, but we took the differential susceptibility. From the differential susceptibility, we proved that the exact Néel temperature is 30 Kelvin, closely matching with the Russian group reported in 1982. So what we figured out that in the nanostructures, of course, the temperature pushed to the even lower temperature side, the Néel temperature. It is necessary to do the differential susceptibility analysis to figure out the exact magnetic ordering. Till this particular 2008, our report, people thought that, okay, 40 Kelvin is the Néel temperature, but it's not the 40 Kelvin. Instead, it is 30 Kelvin, and excellent agreement with 29.5 Kelvin by the Russian group, because the heat capacity data is closely related to the function of the multiplication of this susceptibility, magnetic susceptibility, with the temperature and its derivative. So yes, of course, at low temperatures, these systems shows the heat capacity T-square dependence. In our case, the log plot, this slope is nearly 1.91 Kelvin in this CO2 TiO4 case. So such kind of T-square dependence generally gives the signatures of the spin liquid excitations. Yes, the low temperature part is completely competing magnetic exchange interactions are there, and long range ordering is destroyed, but it still follows some kind of dynamics, and then the spin liquid state is evident from the heat capacity data. So these results are complemented by the error plot analysis. That means we took the series of magnetization isotherms at different temperatures close to the ordering temperature. Generally, this error plot analysis is useful to distinguish whether it is the first order type of transition or the second order type of transition, depending upon the slope. So higher isotherms, higher temperature isotherms, they show the perfect positive slope. But when we go to the lower temperatures, you can see the slope variation is there. So this type of slope variation is giving the signatures of the system contains, is going pseudo first order nature of the transitions, which we can't able to see in either of the measurement techniques, but indirectly from the MH isotherms. And this result is further complemented from the magnetization versus isotherms, as well as uh, the change in the magnetic entropy versus temperature. We can see the perfect zero crossover of the magnetic entropy change when we are going towards the lower temperature side. And we can see the signatures of the zero crossover at the ferrimagnetic state. And then when it is going to the re-entered glassy state, we can see the compensation point. Across the compensation point, the magnetic entropy change that goes to the lower values and switch up at the lower temperatures. We obtained this change in the magnetic entropy change using the Maxwell equations and the statistical mechanics that we see for a field change of nearly a 5 Tesla that we can see both upside as well as down cycle. That means we measure the isotherms while cooling as well as while heating. We can see the slight hysteresis here that is related to the pseudo first order nature of this particular transition. Well, so magnetization versus field, the asymptotic asymmetry in this particular loop, popularly known as the exchange bias. When we apply the positive field, the loop switches to the opposite to the field. When we apply the negative field, you can see the opposite switching of this particular loop. Though these loops are minor loops, that means it's not completely saturating, but you can see the fatness of this particular loop is very high, representing the very high coercivities and the exchange bias that we evaluated from the formulas listed bottom of this particular slide. So one important thing that we wish to stress is that these exchange bias, the loop asymmetry representing the degree of loop asymmetry, and then the coercivities, they are switchable. Basically they are showing the bipolar nature in the nature, and then we can see one-to-one coincidence of the ordering temperatures in the temperature dependence of the coercivity and the exchange bias as well. So these results are connected with the pseudo first order transitions that we saw on this particular system. So these are the two systems that we investigated, but during this pandemic time, we also investigated a very interesting similar family. The CO2RuO4 belongs to the same family of this particular system. That is CO2RuO4, ruthenium having here same 3+ spin, but it shows the antiferromagnetic properties instead of the ferrimagnetic properties that we saw the two systems. We call it as a glassy antiferromagnetic system. Yeah, it shows the spin glass as well as the antiferromagnetic nature, but very close window of the temperature that we can see. It is evident from the modified Curie-Weiss law. Having the negative theta values, we evaluated the experimental and theoretically obtained magnetic moments are in perfect agreement with slight change due to the ruthenium spin here. But it is possible if the hidden antiferromagnetic ordering is there inside the system, we can lift the degeneracy by applying the very high magnetic field that we did here. We went to till 5 kiloair to the 30 kiloair states. You can clearly distinguish the two peak nature, one corresponding to the antiferromagnetic properties and other corresponding to the glassy nature in the differential susceptibility curves. So what we figured out from this particular study is that if you have from the HT phase diagram, field and temperature phase diagram, when you are in the low field side, it's hardly able to distinguish the AFM and the glassy state. But if you are going to the high field state, you can clearly able to distinguish all the three different phases, paramagnetic, antiferromagnetic, and glassy state. So present in the system. So what we did is that we applied the same Dialman-Thouless analysis instead of AC, we did this to the DC case, and we figured out that the exponent, that phi that we see, if it is perfectly 3, then it follows the mean field AT line. But in the present case, it is deviating from the 3. So non-mean field analysis is needed in order to deal such kind of systems. So another very important thing is that estimation of the exchange interactions. So this system contains the, of course, the exchange interaction, competing exchange interactions. But one way to yield quantitative analysis of the exchange interactions is that apply the high temperature series expressions to it, obtain the coefficients depending upon the different lattice structure and the calculations, and we fitted this particular high temperature part both using high temperature series of different Curie constants, and then the modified Curie is fit. From this particular graph, paramagnetic susceptibility versus temperature, the HTS for C equal to 1.9 perfectly agrees with J1 equal to 5.4 Kelvin, because we fitted until this particular point. When there is a non-linearities in the system below this particular point, we can't able to fit. So we don't have any idea about the exchange interactions present in the system, except we have to go to the theoretical analysis. And we did the same analysis by applying the two different paths. One is AOA cations, both the cations AOA and AOBOA. So using these two unknowns, Z1, Z2, Z1, Z2, we obtained the overall exchange constants, that is 6.8 and 1.26. So 6.8 is agreeing with the 5.8 Kelvin that we got completely from the different technique in this system. So of course, the frequency dependence analysis also provides the glassy nature of this particular system, including all the studies that we have done in the earlier systems, the temperature dependence of exchange bias, zero crossover, very high coercivity fields in this particular system. So the last part is the field-induced transitions in similar family of this particular compound is cobalt orthogermanate. It's very interesting system in the sense that this field-induced transitions are connected with the structural transition that it exhibits across 16 Kelvin from cubic to the tetragonality. So we cannot rule out the Jahn-Teller effect present in this particular system, because you have CO2 plus there in the system. So the field-induced transitions that we saw here in this particular graph, magnetization versus field, you can see the snake-like turn, this particular upturn here in this M versus H. In order to figure out the definite change, we took the differentiation of this magnetization. We can see clearly distinguish all the three different field-induced transitions, which we plotted in the three-dimensional graph at different temperatures. As we are increasing the temperature at certain particular point, you can see that this field-induced transition due to the domain structure is vanished out, and we have one HC1 is present. So this kind of field-induced transitions are occurring when the spins in the Kagome lattice having up spins on one particular layer, the triangular layer, and the another layer is having the down spins in different orientation. Okay, so at lower fields, you cannot expect that all the spins are oriented in one particular direction, but the lower temperatures, what we saw that the domain orientation is playing a key role. That's the reason why you got this particular transition, field-induced transition. But when we are going to the higher field side, okay, you can see that HC1, it is due to the triangular spins. Those are along the H direction, but the spins in the neighboring Kagome is opposite direction. Okay, so final very high fields, at the high fields H, you see that HC2 basically, and all the spins are in the field direction. So this kind of HT phase diagram clearly distinguishes the mixed phases present in the system. So it is HT phase diagram having the canted type of structure, and different fields, we can see different spin arrangement. Yeah, so I'm almost done. I'll conclude with the summary here. I summarize that it is very important to probe the exotic magnetic structure of the strongly correlated systems by picking up appropriate transition element oxides, okay, and see what type of magnetic ordering is there. Okay, that's what I summarize in this final slide, all the results what we obtained. And I finally thank my collaborators, IFW Dresden, West Virginia University, Uppsala University, CNRS Labs France, and within India, UGC DAE, and then IISc Bangalore. A special thanks to the Helmholtz gent from Berlin. And I also thank the FIST2 and then Parameshan supercomputing facilities, because we did some theoretical analysis on the basis of DFT in collaboration with Professor Ghosh. I haven't shown those results yet. Thank you very much for patiently listening my lecture.
Thank you very much.
Yeah.
We may accept one or two short questions, if any. Is there any? Then I have one very short question. Is there any pressure experiment on this material?
You mean to say a neutron diffraction studies?
Pressure,
okay. Oh, pressure dependent studies. Yeah, we haven't done pressure dependent studies, but that will be interesting. We can see the decrease in the ordering temperatures because the atom distances will vary when we apply the high pressure. That is very interesting. So we haven't performed those. Hopefully in collaboration with TokyoTech in future we may.
Thank you very much. Let's thank him again, and let's thank all the three speakers in this session. Thank you very much.
Okay, so we thank you very much, Professor Saito. We come to the photo session. So would please everybody, if possible, turn on your camera and show your faces.
Can you see my video?
Yes.
Yeah.
Yes, I do.
So everybody else, please turn on your videos, the participants. So all the participants.
Yeah. Let's wait half a minute.
Yeah.
Small participants, very good.
So Professor Kuze, you're not visible.
I couldn't see Professor Kuze yet.
Well. Very good point. I forgot. Okay, so a few, maybe, yeah, you have problems with the camera. So yeah, I have most of the people. So maybe I take twice. Okay. So please smile, and 1, 2, 3. And well, everybody can take one. Okay, another one. More participants. So let's wait a while. Okay, so everybody. Okay, so are you ready? Yes, seems. So one more time. Well, two more pictures. Okay, please smile, please. And one more. 1, 2, 3. Okay, thank you very much. So yeah, we resume tomorrow. Yeah.
Thank you.
Same time, and
yeah,
thank you very much.
Thank you very much.
Thank you.
Thanks to all the speakers, chairpersons, and the participants.
Thank you very much.